Welcome Astronomy 1020 Summer 2 to our first office hour session where we are going to do some homework problems together. The homework assignment are problems from Chapter 1 and Chapter 2, and I've provided you those questions. I want you guys to have them in the background on your screen so I can get you to read some of those problems. So I'm sharing my screen with you once again, and let me show you what to do. You go to the Homework tab, and this is our Homework 1. 2 questions from Chapter 1, 3 questions from Chapter 2. If you want the questions, you can right-click on these PDFs. This is the PDF for Chapter 1, and this is the PDF for Chapter 2. And you guys want to have those up so you can read the questions along with me. I am going to put some stuff up on the board here. So what I need from you is obviously get your name on that page in case somehow the file gets disassociated from your email. This is homework number 1. And then we'll also write down the questions. From Chapter 1, we have 42 and 49. From Chapter 2, we'll be doing problems 53, 55, 58. Now you're going to be turning this into me as is, so try to model your paper after what I'm doing up here on the board. Let me go into my lock speaker view. So you can keep it inside your notebook. You won't actually have to submit the file to me, but just for kicks and giggles, put your name, put homework 1, and put the problems. That means later on when you use it as a study guide, you'll know what the hell you were doing. Jordan.
Yeah.
Yemercy, do you have your Casio calculator?
I have this app in the phone that looks almost similar to it. I don't know if you can see it properly.
Yeah, you know, you can use it, but it's a second choice mechanism, my friend.
Yeah.
If I were you, I know it sucks buying stuff, but I would strongly recommend that this weekend you go to Walmart and you shell out 9 lousy bucks. That's about the price of a pack of smokes for one of these Casios. It'll make you follow me better. We're going to start using more advanced buttons as we go. And the buttons here will not exactly match the buttons there. What you have is like, it's like a Band-Aid. It's good for a pinch, but it's not going to do the job, okay? Yemercy, what about you? What's your deal?
It's on its way today. I'm getting it today.
That is wonderful. Maybe like the FedEx guy could drop it into your hands while class is happening. That would be pretty epic, right?
Yeah, I should be receiving it shortly.
Cool. All right, in the meantime, you're going to need something for this office hour, so you're going to have to do what Jordan did. Jordan, which app did you download? P-Calc Lite or something? Or?
Oh, let me see the name again. It's called...
Did you use Pan eCal? It's not great, but... So do you have
I'm sorry, I actually go on Google and put in scientific calculator, and it gives me all the keys that your calculator has.
All right, so do you know how to take a 4th root on it?
I'm sorry?
Do you know how to take a 4th root with that thing?
Not the 4th root, but...
I'm just trying to figure out what you know. That's sort of my litmus test. If a person knows how to take a 4th root on their own, then I will not need to be giving them lots of instruction. If they don't, I will. So can you tell me what your link is so I can follow with you? Because I'm going to have to help you. So what's your, what did you type in and what link are you at? Jordan, can you tell me the name of the app you're using?
Are
you using this? Do you see what I have up here? Is this what you're using, Yemercy? Look at my screen. That's what you're using. Okay. I just want to have it as reference. Jordan, can you show me your app on your phone? I just want to see what the heck you're doing.
So it's called Hyper Scientific Calculator.
Hyper
And it
Science.
looks like
Is this a Google or an iPhone app?
Google.
Google. Okay, shoot. All right, I can't do that. All right, let's get into it, guys. Yimmersy, I'm going to need your help here. I need you to help me read a problem. Chapter 142, what's it say? You read it, I read it. And you guys should be copying exactly what I do. What's the title of the problem?
Sorry, I had you on mute.
Yep.
Scaling and local group of galaxies.
Okay, hit me one time.
All right, so both the Milky Way galaxy and the Andromeda galaxy.
Andromeda.
Andromeda, okay. Galaxy M31 have a diameter of about 100,000 light years. The distance between the two galaxies is about 2.5 million light years.
Let's pause there. How do I put 2.5 million into scientific notation from Tuesday's lecture? See, I need to, can I explain what I'm doing right here, Yimmersy, so you can understand my thoughts? In every problem, you are given some numbers that you can work with. And these numbers, what they're called, is they are called the givens. The givens are what you're assumed you can work with to solve problems. I find from years of solving problems that it's a good idea to get your givens down on the paper so you can kind of see what you have to work with. It's kind of the equivalent of like chopping your peppers and onions before you start to cook the pasta. You've got a little bowl with all of your ingredients and now you're ready to go when you're cooking, right? So I want to write down 2.5 million, but I don't want to write it in words. I want to write it in numbers. Can you translate that into scientific notation for me?
Yeah, 2.5 times 10 to the power 6.
Yes. You are impressing me this morning. I'm loving it. Okay, continue on your reading.
A, using a scale on which 1 centimeter represents 100,000 light years, draw a sketch showing both galaxies and the distance between them to scale.
What they've just done for us is they've given us a scale factor in which 1 centimeter primed is equal to 100,000 light years. Now let's test your memories. Do you guys remember why I chose to use the prime symbol?
This is fake centimeters.
Yes, that's right, Jordan. And why am I worried about fake centimeters again? Do you remember the concept of why I want to call them fake centimeters versus real centimeters?
Not sure.
Well, believe it or not, Jordan, in professional astronomy, the favorite unit of distance that we use in our own personal calculations is centimeters. So it's not unheard of for an astronomer to convert 100,000 light years actually into centimeters before they do math. But the problem with that, Jordan, is do you really believe that 1 centimeter is 100,000 light years long?
No.
Exactly. So what I'm worried about is if we start converting these into other units, I might get confused, Jordan, between what is my scale model on the piece of paper and what is real distances in space. For instance, I could convert this into centimeters, and then I'd have this weird looking equation where 1 centimeter equals some much greater number of centimeters. And since centimeters were on both sides, I would get confused about what's real and what's fake. You see what I'm saying?
Yeah.
This issue comes up, and it might even come up in our problem. All right, anyways. The point of that is just to remind you why we have the fake centimeters. All right. What did it ask us to do again, Yimmersy? I'm getting lost here.
Using a scale on which 1 centimeter represents 100,000 light years, draw a sketch showing both galaxies and the distance between them to scale.
We actually have to draw this thing to scale. Now, it would be very helpful if you guys had a simple plastic ruler. These cost about 20 cents at your local drugstore. Or if you're an Amazon type, you can order it on Amazon. Yemmercy, Jordan, do you have such a ruler laying around your house with centimeters on it?
Somewhere, right here. Small.
Oh, hell yeah. That's got centimeters on it. Nice. Yemmercy, you do not, huh?
No.
Well, this is going to suck then, okay? I would like to point out, I don't know if this is true for you, my pinky finger, the width of my pinky fingernail is about 1 centimeter. Can you see that?
Yeah.
So you're gonna have to you're gonna have to use you need to find an object, we call it a straight edge, something that's straight around your house. It could be the side of a box or a coaster. You're gonna need to make some lines with me. Can you find something straight? Could be a hard book, could be something.
Yes, I can.
All right. So what we're gonna do is we're gonna start by making one of our galaxies up here in the corner. I want it to be 1 centimeter. I want it to be pretty damn close, CMC. So one way we can make a galaxy is we make a line like this, okay? And then this is 1 centimeter. To turn it into a galaxy, an old cartoon trick is to put a bulge in the center and then put some spiral arms. That's kind of like a barred spiral galaxy. And I'm going to label it as 1 centimeter prime. And my next goal is to figure out how far away I should draw this line. Here's a hint. It's going to end up being a really big line all the way across your paper. Yemmercy, Jordan, we have a scale in which 1 centimeter is equal to 100,000 light years. We need to figure out how far away 2.5 million light years would be in fake centimeters. What's the technique that we're going to use to do this?
Dimensional analysis.
Hell yeah. Right on point, son. Okay, can you walk me through your 4 steps of dimensional analysis, Jordan? Find the smiley face, and I want you to read me step 1.
Write down the number to cover with the unit.
So Jordan, which number is that with its units?
It will be the distance.
Yes,
2.5 times 10 to the power of 6 light years.
Excellent. Okay, step 1 done. Follow along with me, guys. Write down what I write down. Okay, step 2, Jordan.
Multiply by a division bar.
That's easy. Bam, just did it. Step 3, Jordan.
Put the unit first to cancel.
All right, here's where it's your time to shine. This is the important part. I need some units on top and I need some units on bottom. What am I going to put?
On top, you're going to put the centimeters.
Real centimeters or fake centimeters?
Fake centimeters.
Perfect. And on
the bottom, it will be light years.
Exactly. That way light years cancels out. Let's do that so we remind ourselves. That's why we did that, to cancel out light years. Okay, step 4.
Put the number in the second using conversion factors.
Okay, now it's up to you. We got to put a number on top and a number on bottom. Tell me which goes where.
The light years, the 100,000 light years on the bottom.
Correct.
1 centimeter on top.
What do I put on the top? I'm sorry?
1 centimeter, 1 fake centimeter.
Wow. Jordan, I'm starting to think someone understands me. That's a terrifying thought. I'm not used to that happening. Okay, so Jordan, I think you get me. Now it's time to test out your crappy calculator substitutes, which are not Casio FX60 260 solars, but give it a whack anyways. I'm going to do 2.5 EXP6. Nobody's typing times 10, right? Typing times 10 is for amateurs. Okay, use your EXP key. 2.5 exp6. If it makes you feel good to multiply 1, well, just go ahead and do that. The rest of us are going to move on and divide by 100,000.
It will be 25.
Good.
Yes.
And the units?
Fake centimeters.
Okay. Class, in each problem, I grade them on a 5-point basis, okay? And I, in my mind, have assigned what the points are worth. You've just earned 1 out of 5 points by showing me this work of how far away the galaxies are in fake centimeters using dimensional analysis. That earned you a point. Another point was gained from drawing the galaxy correctly with a length of 1 centimeter. Oh, and by the way, I want you to know I got a ruler and I'm not above measuring it on your paper, so watch out. Okay, now we have to make a line that's 25 centimeters long. That's going to be a bit of a challenge for you, Yimmersi, because you don't have an actual ruler. Now, there's no reason to believe my hand is the same as yours. If I put my pointy finger at 25 centimeters, the 0 comes down sort of to here on my wrist. But that's not a standard unit of length. What are we doing? Feet, the king's foot? I don't know. 25 centimeters. What would you have in your house that was 20? Maybe a butter knife? Some takeout chopsticks and a steak knife.
Will that even fit on the paper?
We're gonna have to talk about how to do that. Holy jumping Jesus. It looks like a steak knife is about 23 centimeters long. Chopsticks in the package are about 25 centimeters long. Okay, just giving you some objects around your house that you might be able to relate to. Jordan, let me address that. Jordan, in order to fit this on your paper, it's going to be tough, but watch me. I found that if you put the first galaxy in the wicked upper left-hand corner of the page, and then we're going to have to go diagonal all the way down. If your notebook is big enough, you might be able to fit the whole damn thing on it, okay? And now down here, make another 1 centimeter line. Ouch. Sorry, lamp. Okay. And then kind of make your bulge and draw in your spiral arms. Let's label this as 25 fake centimeters, 2.5 million years, all right? Jordan, did it fit on your page if you did it diagonal?
Yeah.
Show me. Hold your paper up so I can see what you're doing.
I just have to take that from here, but that will be the...
Back a little bit. That looks pretty good. Now remember, you need another...
I just have to put the...
Oh, yeah, you got to put the galaxy on each side. Make it 1 centimeter. Yimmersi, show me what you got. Can you hold up your work? I want to critique it. That's good. Your 1 centimeter looks a little big, but do you see those 2 lines in your paper? Yimmersi, I'm going to assume that your lined notebook is similar to mine. Just to help you out here. One centimeter is a little bit more than 1 line. Do you see that? 1 centimeter is like a line and a half. So I think your galaxies are a teensy bit longer than 1 centimeter, but that's me being picky. Did you use pencil or pen? Pen? Well, that was a mistake. You might want to, great. If you're using pen, you might want to start switching over to pencil. If I have students doing stuff in my presence, I don't even let them mess around with pens. Pencils only, because I don't know any perfect people. I don't know if you do. All right. Read us part B, Emercy.
How does the separation between galaxies compare to the separation between stars?
All right, stop there. Wait, stop there. Let's answer that question first. How does the separation between galaxies compare to the separation between stars? Do you guys remember what the closest star to Earth is? Oh, okay, that's the sun. Do you remember what the closest star to the sun is? Did I tell you in our first lecture?
Sure about. I don't think so. Maybe I'm wrong.
I'm sorry, Jordan, can you say it louder?
I say I don't think so. Maybe I'm wrong.
Oh. It's Alpha Centauri. Alpha Centauri is 4.4 light years away. How does the separation between galaxies compare to the separation between stars?
Much closer.
Say that?
Much closer.
That's a little vague, Jordan. What's much closer?
Light years. So.
What are you saying? What is much closer than what?
The distance between stars
Is
in light years is closer than the distance between galaxies.
correct. By approximately sort of what factor? Why don't you pretend 2.5 is the same thing as 4.4, because they're almost the same thing. $2.50 is close to $4.40. But you know it's not the same? 10 to the power of 6. The distances between stars are millions of times smaller or closer, either way, than the distances between galaxies. We're assuming that the typical separation between galaxies is similar to a typical separation between, we're assuming that this is a representative distance between galaxies, and we are assuming that this is a representative distance between stars. Okay, Yimmersi, that's one of our subparts. What's the next part of B?
Based on your answer, discuss the likelihood of galactic collisions in comparison to the likelihood of stellar collision.
In other words, Yimmersi, it's asking us this question. What's more likely to collide, 2 galaxies or 2 stars? What do you guys think? Am I more likely to have 2 galaxies collide or 2 stars collide?
2 stars.
You'd think so, wouldn't you, Jordan? Because 4 sounds like a
Yeah.
lot less than 2 million, right? What if I told you it wasn't
Oh.
true? You'd be surprised, wouldn't you? The thing is, Jordan, you're pretty good at dimensional analysis, but they didn't ask you to do part A for stars. They only asked you to do part A for galaxies. Isn't that funny? They wanted you to compare the likelihood of a galaxy collision to the likelihood of a stellar collision, but they only asked you to do a scale model for galaxies. What if they had asked you to do so for stars? First of all, it would have been a little more complicated, and here's why. The sun has a diameter of 1.4 million kilometers. You might remember that from our lecture last week. That was a fact in our scale model. What if we had pegged the diameter of a star to 1 fake centimeter? How far away would the neighboring star be? Now, Jordan, normally I'd want you to do the dimensional analysis, but I'm concerned about time, so I'm going to do it for you, okay? Let's take 1.4 million kilometers. Sorry, not 1.4 million kilometers. The distance between stars is 4.4 light years. That's what I want to convert to fake centimeters. So I would first convert 4.4 light years into kilometers. You guys can remember by looking into your notebooks that 1 light year is 9.5 trillion, 9.5 trillion kilometers. And then I would convert the kilometers into fake centimeters by doing 1 fake centimeter is 1.4 million kilometers. Sorry, I'm kind of running out of board space, so that might be a bit squishy for you guys. So let's do the calculation together, Jordan and Yimmersy. I'm going to do 4.4. I'm going to times it by 9.5 trillion, exp12. But now I'm going to divide it by 1.4 million. Let's look at that number. Count with me. 1, 2, 3, 4, 5, 6. That's pretty darn close to 30 million fake centimeters. So I ask you again, Jordan, why didn't they ask you to do part A for stars, where the diameter of the sun was 1 centimeter?
Well,
Did I lose you?
For a second. Yeah, I will blame.
I went too fast for you. Jordan, we made a scale model of galaxies in which we set a galaxy, normally 100,000 light years, to a size of 1 centimeter. And then we just asked, how far away was the next galaxy? And we found it was 25 centimeters, correct?
Yeah.
If we had played the same game with a star, and we had made the diameter of our sun 1 centimeter, the next star would be 30 million centimeters away. That's like 300 kilometers. 300 kilometers is like the distance from here to New Hampshire, maybe even Maine. So Jordan, they didn't ask you to do part A for stars because you would have needed a piece of paper the size of New England.
Yeah, way bigger than the distance between the galaxies.
Well, that's not exactly a correct statement.
Oh.
Because it is not true that stars are closer than galaxies, because 2.5 million is much greater than 4.4. But to scale, this is about a distance to diameter ratio. Look up here for a second. It's diameter to distance, okay? For galaxies, their diameter to distance ratio is a 1 to 25. For stars, their diameter to distance ratio is a 1 to 30 million. So why is it then that stars are less likely to collide than galaxies? Stars might be closer, but relative to their diameters, they're farther apart. Let's answer that down here. However, stars are less likely to collide than galaxies because the distance to diameter ratio for stars is millions of times greater than, well, we'll just say galaxies. Millions of times greater than galaxies. Get all that down. Jordan, Yimmersi, do you have it down?
No, a little bit.
You need to know the second, Jordan?
Yes.
Let me know when you're done.
Done.
Okay, I'm erasing. All right, 1 down, 4 to go. Jordan, do you want to read us chapter 1, number 49?
49. Oh. Sorry.
Read me the title too.
Universal scale.
Okay.
Suppose we want to make a scale model of a local group of galaxies in which the Milky Way galaxy was the size of a marble, about 1 centimeter of diameter.
And we remember from the previous problem that the diameter of the Milky Way is 100,000 light years. So basically they're telling us we're going to use the same scale factor as the first question.
How far from the Milky Way galaxy will be the Andromeda galaxy be on this scale?
Hold on, Jordan, let's just take it one step at a time. So the first one was part A, right?
Yeah.
Plus, it's very important that you label A's, B's, and C's so I can follow your work. So they want to know Milky Way to Andromeda on the scale. And this sounds very familiar. This is what we did in part A of problem 42. So let me remind you what we did. We took the distance which was 2.5 million light years. We then did dimensional analysis. We made a division bar. We put light years on the bottom. We put fake centimeters on top. 1 fake centimeter is equal to 100,000 light years. We canceled out our light years, and what did we get, Jordan?
Oh, 25
fake centimeters.
fake centimeters.
Put a box around that. That's a classy move. Okay, now we can go on to part B.
Oh, how far will the sun be from Alpha Centauri?
Alpha Centauri. That's kind of a weird thing.
On this scale.
Alpha Centauri.
Alpha Centauri.
Mm-hmm. That sounds good. If you grew up as a sci-fi nerd like me, and I loved to read science fiction novels and I liked to watch science fiction movies, Alpha Centauri shows up a lot. Sorry, I'm blocking your view. Alpha Centauri shows up a lot in science fiction books and movies because it's the nearest star, so people are always traveling to it in these wild adventure stories. All right, how far away was Alpha Centauri again?
4.4
light years.
light years, yeah.
Okay, Yimmercy, I just did step 1 of dimensional analysis for you. What's step 2?
Step 2 is multiply by division bar.
Beautiful. What's step 3?
Put units first to cancel.
Give me some units.
So it will be fake centimeters on top.
Yep.
And then light years in the bottom.
Okay. Step 4.
Put the numbers in using conversion factor and split.
Okay, so give me that stuff.
All right, so it'll be 1 fake centimeter on top.
Yep.
And then 100,000 light years in the bottom.
All right. All right, so do the math and tell me what you get. You guys punch it up and tell me what the answer is. I'm gonna bounce rainbow ball while you do that.
It's really long.
You got something?
Times 10 to the negative 5.
All right, so I'm gonna start getting good at dribbling while I'm waiting for you to calculate this thing. There is no reason I should be good at any sport.
I have 0. I think I did it right. 0.00004.
Whoa, 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 whoa. That sounds like a job for dimensional analysis, Yimmercy.
Yeah.
Could I get that in dimensional analysis?
Sure. So
4.4 times 10 to the negative 5.
Excellent. 4.4 times 10 to the minus 5. What are the units, Jordan?
Fake centimeters.
Killer. Notice that on the same universe, this is kind of the other converse to the problem we did earlier. if the distance to diameter ratio for galaxies is 25, on the same scale, it's 4.4 versus 4.4 times 10 to the minus 5. Something weird about that. Oh yeah, it's not 1. It's 4 over 4.4 times 10 to the minus 5. If you take the ratio, that's 1 part in 10 to the 6. That's what I'm thinking. 1 part in 10 to the 6. It's basically a 1-to-1. Actually, oh no, because it's in fake centimeters. Never mind. Okay, I'm just thinking out loud. What's part C?
See, how far will it be from the Milky Way galaxy to the most distant galaxy in observable universe?
The observable universe is the most distant galaxies we can see. Let's see, the universe is 13.6 billion years old. So the most distant galaxies that I could see would be 13.6 billion light years away. 13.6. How many zeros are in a billion, class?
Nine.
Okay. We have 13 times 10 to the 9 light years. Let's do some dimensional analysis, Jordan.
All right. So it'll be
What's step
2
2?
point.
Hold on. I want to set it up first. Give me some units.
All right. 2 point.
Nope. Nope. Units first, numbers second.
Oh yeah. Centimeters on top. Fake
Yep.
centimeters on top. Light years on bottom.
What's my conversion?
So 1 to on 2.5
No.
times 10 to
We're still
the
using the
6.
same scale, Jordan, up here.
Oh, wow. 100,000 light years.
Okay, so punch it up.
Oh, maybe 136 to the 10 to the third. 136 times 10 to the third. 136,000.
That number's less than a million, Jordan, so you don't need to put it in scientific notation.
Okay, so it's 136,000
Units?
fake centimeters.
And that is problem number 49.
Oh, 13.
Jordan, let me know when you're done writing.
You can get it over with.
Say that.
I'm done.
All right. Yimmersey, let's go to chapter 2, number 53.
All right, Earth rotation speed.
No, chapter 2. You're still in chapter.
Chapter 2, sorry.
You want the other PDF.
Arc minutes and arc seconds.
Okay. Do you guys remember the conversions for arc minutes and arc seconds? Let's write them down.
I'll find the registration.
Sorry? 1 degree is equal to 60 arc minutes. And our other conversion is 1 arc minute is equal to 60 arc seconds. Let's get those down in the corner. We're going to need them. Okay, Yimmersey, when you're ready, read us the whole thing. Up to part A.
There are 360 degrees in a full circle. Part A, how many arc minutes are in a full circle?
Okay. Let's start with what we want to convert. What's step 1, Yimmersey?
So you wanna, step 1, let's see.
Of dimensional analysis.
Is write down number to convert with its units.
So what number should I write down?
So 360 degrees.
Excellent. What's step 2?
Multiply by division bar.
Step 3.
Put units first to cancel.
Okay, give me some units top and bottom.
So you will have 60 degrees.
No,
I mean 60.
No. Whoa. Check yourself before you wreck yourself. You are not allowed to talk numbers to me. I don't want to hear about numbers. That's the mistake. You want to talk units, just units, no numbers. So tell me what units to put top and bottom.
The arc minutes on top.
Very good.
And then degrees on the bottom.
Now you're talking. Now you're talking the good talk. Let's cancel out degrees, Yimmersey. This helps us remember why we do what we do. Okay, you might think I'm being silly, but I promise you I'm not. I mean, I'm being silly, but I'm also making a really good point, okay? So what's step 4?
Put the numbers in using conversion factor.
Okay, there's some conversion factors. Tell me numbers top and bottom.
60 on top and then 1 in the bottom.
Nice. Okay. Punch them up with your calculator and tell me what the answer is.
I have 21.600.
Is your number greater or less than 1,000,000?
Less than?
Then you don't need to use scientific notation.
Okay. So 21,600.
Units?
Arc minutes.
Okay, I can read the manual there.
Box it up. That's a classy move. Part B. Yimmersey, part B? You might be muted.
Yeah. How many arc seconds are in a full circle?
All right, how do we want to tackle this one?
You're gonna take the 21,600 arc minutes
Yep.
times 60 arc seconds.
Let's do units first.
Okay. Arc seconds in the top,
Yep.
degrees on the bottom.
Degrees? I don't know.
Arc minutes. I'm saying arc minutes. Sorry.
Yes. Okay. Now you can give me your precious numbers.
I just have to convert it. Hold on.
No, you don't. Whoa. Yimmersey. Slow down. Arc seconds to arc minutes.
Oh,
Right?
I'm going a step ahead. Sorry.
You've got a conversion here. You're actually going a step behind and a step ahead, but that might not make sense to you.
So 60 arc seconds on top and 1 in the bottom. 1 arc minute.
Punch that up for me.
So it'll be 1.296 times 10 to the power of 6 arc seconds.
Beautiful. Watch your notation. Don't make that look like 611. Be careful there. But you did good, Yimmersey. You did good. Part C.
What distance is oh, wait, wrong one. The moon's angular size is about 1/2 degrees. What is the arc minutes in arc seconds?
We first have to convert this to arc minutes, and then we have to convert it to arc seconds. Jordan, why don't you help us through this one? Walk me through what I do.
So we put the the 0.5 degree
Okay.
times division bar.
Excellent, sir. I like the way you move.
So in units will be on top arc seconds.
Well, we have to do both. We have to convert it to arc minutes, and we have to convert it to arc seconds. You can do either way you want, but I recommend the arc minutes first.
Arc minutes on top. Degrees on the bottom. So 60 on top.
Yep.
1 on the bottom.
Excellent. Can you do that in your head, buddy? If not, use your calculator, but I thought you might be able to do that in your head.
30.
Sorry?
30.
30. 30 what?
Arc minutes.
Cool. All right, there's one of our answers. What do we do next?
So now we have to convert the 30 arc minutes to arc seconds.
Okay. We'll do that in the next line. Units?
Arc seconds on top.
Yep.
Arc minutes on the bottom.
Yep.
60 on top, 1 on the bottom.
What do you get?
Uh, 1,800
Units?
arc seconds.
And that's, my friend, is how we make it to pizza, right there. Number 53 has been completed. Jordan, I'll give you a second to catch up.
You can erase it.
Okay. Our next problem, oh, actually, let me get into our next problem here. Chapter 2, number 55. I have taught you about arc minutes and arc seconds, but you haven't used them too much yet. So in the following problem, we're going to be given an angle in degrees, and we're going to try to convert it into a particular format. It's the format that we list stellar coordinates in. And you're going to be learning about stellar coordinates in today's lecture. So let me share a screen and give you an example. Let's say we went to a famous star, one that's up in our sky right now, named Arcturus. Arcturus is in the constellation Boötes. If you look up its stellar coordinates on Wikipedia, I want you to notice the formats that they give them in. Where am I here? Control plus, plus, plus. You'll notice that the coordinates, at least for declination, are listed in this funky format where they give you the number of degrees, and rather than give you 19.2196754 degrees, they subdivide it into 19 degrees, 10 arc minutes, and 56 seconds of arc. That format is also used in coordinates on Earth if you do your latitude and longitude. For instance, on my iPhone, Jordan, I know you've got a Google phone, but you probably have a similar thing. I have a compass app. And on my compass app, it gives me my latitude and longitude in the exact same format. 40, it's probably not in focus for you guys. It's 40, I could adjust my focus, but it's actually good right now, so I don't want to mess that. It's 41 degrees, 49 arc minutes, and 23 arc seconds. This is just a standard format they use for angles. So with that in mind, Jordan, could you read us the title and the instructions for number 55? Sorry, Jordan, you're muted. It looked like you were talking to me.
Angular conversions.
You're good at conversions, not reading? Is that what you're implying?
Yeah.
Well, unfortunately, Jordan, you and Yimmersey are the only people who are like talking to me. So you're up. Think of this as a good time to practice your thespian articulations, okay? Your dramatis personae.
God, Lord. Angular conversion.
Okay.
1. That's what it says.
Angular conversion 1. Yep. I like it. I like your voice. It's nice.
The following angles are given in degrees and fractions of degrees.
Okay.
Rewrite them in degrees, arc minutes, and arc seconds.
In other words, Jordan, if you look at my visual interpretation of what you just said, we're going to start with some number of degrees. We're going to convert them into a format where it's degrees, arc minutes, and arc seconds. Once you've got that down, you may proceed to read.
So,
I'm going to take coffee.
well, what else we have is like A, B, C, D, and E,
Okay.
and the degrees.
So A, how many degrees do we have?
24.3 degrees.
So you guys may not know exactly how to do this, so I'm going to walk you through the first one, and then you guys are going to do the rest of them for me. Do you guys see that I can already identify that I have 24 whole degrees? So for my format on the right, I've got 24 degrees. And I'm going to want to have some arc minutes and arc seconds as well. So now that I have 24 degrees, the remainder is 0.3 degrees. Jordan, help me convert that, since you're good at conversions, into arc minutes, please. I've done
So
step one for you.
0.3 times division bar.
Yep.
On top arc minutes, on the bottom degrees.
Yep.
Will be on top 60.
Yep.
Bottom one. And boy, oh boy. 18.
Okay.
Arc minutes.
So that's what we write in for 18. What should we put in the box for arc seconds?
So now we have to the 18 arc minutes.
No, Jordan. I understand what you're saying, but we think of this like a stellar coordinate, okay?
Mm-hmm.
24.3 degrees. The 0.3 degrees is exactly 18 arc minutes. If this had come out to be 18.792, we'd take the fraction of an arc minute and convert that to arc seconds. But here, we stop perfectly at 18 arc minutes. Does this make any sense, what I'm saying to you? So what we would put here is 0 arc seconds.
0.
Because there's no fraction of an arc minute.
Oh,
right?
okay.
Does that make sense?
Yeah.
Okay. Let's try the next one, and I think this will make more sense as we go. What's part B ask?
So 1.59 degrees.
Okay, Yimmersi, why don't you chime in here? Let's set up our format. We have blank degrees, blank arc minutes, blank arc seconds. So Yimmersi, can I fill in any of these boxes here? You're muted. Yep.
Yeah. So I have 2 degrees.
No. You are not at 2 degrees. You are at 1.59 degrees.
Okay. So 1.6 degrees?
No. So what you're doing is you're rounding. The goal here is not to round. It's to convert 1.59 degrees into a new format. Okay, look. Imagine we did this with hours. Suppose a class was 1.5 hours long. You could convert that into 1 hour and 30 minutes, correct? What if the class was 1.59 hours long? That would be 1 hour, 30 minutes, and some number of seconds. Let's see here. 1.59. 0.59 times 60 would give us 35 minutes with 4 remainder, and 0.4 minutes times 60. So I could write 1.59 hours as 1 hour, 35 minutes, and 24 seconds. Do you see what I'm saying? I'm not rounding to 1.6. I'm starting with 1 degree. And now we want to deal with the 0.59 degrees and make it into arc minutes and arc seconds, like we were converting to hours and minutes. And right now you're thinking, sounds good, so what the fuck do I do, right? Or do you know what to do? Yimmersi, are you frozen? Did we lose internet connection? Oh no. Oh wow, I'm back. I was just having a freak out here. My internet just went kapoots, but then it came back. And you guys are still here, which is great. Sorry about that, guys. I personally blame Cox Communications. All right. Yimmersy, you and I were talking when I lost you, right? Thanks for
Yes.
sticking with me. Hopefully that will never happen again. Last summer session, summer 1, I taught 2 classes, and that only happened to me once. So let's hope that's my one time, okay? Anyways, Yimmersy, we were trying to convert 1.59 degrees into degrees, arc minutes, and arc seconds. We have 1 whole degree, so I've placed that in the slot. Now you got to deal with the 0.59 degrees.
All right, so do I put that, the 0.59?
Think of this as some
Degrees.
change. You need to convert this into start with your point, take the remainder, which is the 0.59 degrees.
Okay.
And now why don't we start by converting that into arc minutes? Can you help me do that?
Yep, so you will times by division bar,
Yes.
60 arc minutes on top,
And on
over,
bottom?
yep, and over 1 degree on the bottom.
Okay. So punch them up. What do I get?
35.4 arc minutes.
Okay. So Jordan, I think you might kind of understand what's going on here. What would I do next, Jordan?
So you will take the 0.4.
Right, but first let's
Convert.
put the 35 whole arc
Oh
minute
yeah.
into the box.
Yeah.
And now we'll take the remainder, the 0.4 arc minutes, and what do I do there?
Times division bar.
Yep.
Arc seconds on top, arc minutes on the bottom, 60 on top, 1 on the bottom, and it
what's
will
that
be
give us?
24. 24 arc seconds.
Nice. So you see, Yimmersy, we kept taking the remainder, the leftover change, and we kept converting that into whole numbers of arc minutes and arc seconds. So these are 2 equivalent ways of describing the position of an object. 1.59 degrees up, or 1 degree, 35 minutes of arc, and 24 seconds of arc. All right. Let's go on to part C. I need to erase part A. Part C.
Oh, 0.1. I spaced out for a moment.
That's degrees, right, Jordan?
Yes.
Well, it looks like we got 0 degrees. 60 arc minutes to 1 degree. I think 60 times 0.1 is 6 arc minutes, giving us
0 arc seconds.
Yep. Do you guys see how I put double zeros here? That's sometimes called cell padding. You sometimes want to make sure all of your numbers have the exact same format. They call that cell padding. Let's move on to D.
0.01
degrees. So 0.01 what do we got there?
It'll be 0 degrees.
Yep, it's 0 degrees. Very good. And now do this conversion.
It will be 0.6.
So that means we have no arc minutes either. And now we'll do the
And
0.6
then
arc minutes times 60 arc seconds.
will be 36.
Huh?
Will be 36 arc seconds.
Yeah, that sounds right. And now up here, we'll do part D.
Oh, 0.001.
Okay, that's at least going to be 0 and 0. Let's convert this right to arc seconds. So Jordan and Yimmersi, I want you to watch some moves I got here, okay? This is an important learning lesson. I can convert this to arc minutes and arc seconds in the same step. I'll do dimensional analysis twice. In the first division bar, degrees on bottom, arc minutes on top. In the second division bar, arc minutes on bottom and arc seconds on top. 60 arc minutes is 1 degree. 60 arc seconds is 1 arc minute. I could see that in the previous problem, 0.01 degrees gave me 0 degrees and 0 arc minutes. So if I have an even smaller number, I'm still going to have 0 degrees and 0 arc minutes. That means I want to get myself right to arc seconds. So why don't you guys do this? 0.001 times 60 times 60. Tell me what you get.
$360.
Hell no. Try again, Jordan.
What did I do? Oh.
Look, if
Heck am I doing?
0.01 degrees is 36 arc seconds, a
Yeah,
10th
yeah, I'm missing 2 zeros in it.
3.6.
Now, that gives us an uneven remainder of arc seconds, but that's okay. We'll list it here anyways. So 3.6 arc seconds. And now 55 is done. We got one more to go. Jordan, let me know when you're finished copying.
All right.
Wow, it looks so beautiful and sunny out right now. Too bad we're stuck in here on our computers, huh? Should be out in the sunshine.
I'm done.
Okay, I'm erasing. Okay, chapter 2, number 58. Yimmersi, do you want to do this one since Jordan read the last one?
Beetlejuice.
Sure, I'll do that right now. Number 15. Beetlejuice diameter.
Okay.
Estimate the diameter of the supergiant star Betelgeuse from its angular diameter of 0.05 arcsecond and distance of about 600 light years. Compare your answers to the size of our sun and the Earth's sun distance.
Compared to the sun, and you guys will remember that the Earth-Sun distance is the same thing as 1 AU. Why don't we draw this picture together? Let me get a circle here. What I need is like a coffee can lid or something. Hold on. Find something to make a little circle with. And we are going to be looking at this star from some distance away. It's going to subtend some angle. We're looking at it from really far away because it's 600 light years. Okay? The diameter of the star Betelgeuse we call S. The angle we call theta. Let's put our eyeball over here so we can remember that we're observers watching from Earth. The distance to the star, astronomers like to use little d for distance. Often because it's an unknown variable. Do you guys remember the formula that relates these three quantities?
Oh.
Is it the angular formula? Small angular formula?
Small angle formula, very good.
Yes. Yes.
S equals theta times d times 2 pi over 360 degrees. Jordan, you seem to have some math instincts. What do you think? What should I do here?
So we'll convert the 0.05 into degree.
Damn, you're good. I didn't think you were going to pick up on that, but you impressed me once again. See, some people would just try to plug the 0.05 arc seconds in. But Jordan can see that ain't going to work because he's got to try to cancel out with degrees. In this formula, theta, the angular size, must be in degrees. They've given it to us, however, in arc seconds. Jordan, at this point, we're pretty good at converting from arc seconds to degrees, aren't we?
Yeah.
So walk me through the doing of that.
So the 0.05
Yep.
arc seconds
Yep.
times division bar.
Yep.
And this time on top is going to be angles.
Wait, what angle? I need units.
Oh, degree.
Uh-huh.
Degree on the bottom arc seconds.
Jordan, that will work if you have a conversion from degrees to arc seconds. Now, I happen to know,
Don't have it.
but I'm not telling you. Do you know how many arc seconds are in a degree? If you don't, why don't we convert to a unit you do know and work our way towards degrees?
All right. Then we go from arc seconds to arc minute. So on top it will be arc minutes.
Yes.
So on top is 60. On bottom 1.
All right, let's keep
Wait.
going. So now our arc seconds cancel. What do I do next?
Oh.
Don't bother
On top
calculating
will
it to the end.
be the arc minute. No. The degrees. The angle. Oh yeah. Degrees. Yeah.
Degree. Where? What's top? What's bottom?
Degree. Top.
And on bottom?
Arc minutes.
Good. Conversion?
On top 1. On the bottom 60.
Okay, punch them up.
Oh, holy moly.
What'd you get?
0.0483.
What?
I don't know what I did here.
You screwed up is what you did.
Yeah.
But I'm not telling you where you screwed up. I want you to figure it out. Also, you should not have come out with 0.048. That's weird. You should have come out with exactly the same thing, 0.05. You messed this up somewhere. You made a classic mistake. Where's your mistake? Yimmersy, if you see where the mistake is, feel free to chime in.
Yeah, because I have no clue about it.
Jordan, why don't you re-examine your conversion factors?
So 0 time, that will be 3 times.
Your units certainly cancel out. The units are good. The problem is with your numbers. Is it true that 1 degree is equal to 60 minutes of arc?
Would it be 360?
No.
Slow. 3.
Is that your calculator? That's so cool. Just in the nick of time, huh? Jordan, you have until she opens up her Casio to figure this out. Otherwise, I'm going to have to tell you what you did wrong. Jordan, you have 1 arc second is equal to 60 arc minutes. That's not true.
Yeah. Well,
1 minute of arc is equal to 60 arc seconds. This is a classic mistake. Yimmersy, you ready to try out that new Casio?
fucking hell.
Okay.
Yes, I am.
Type 0.05, divide by 60, then divide by 60 again. What do you get?
1.3888888889, -5.
Let's talk proper here. Let's round it to 1.4 times 10 to the -5. What are my units?
Degrees.
Good. Don't make it look like -50. Make it look like degrees. Jordan, do you see this 600 light years?
Yeah.
If I plug that in for distance, I'm going to get the diameter of my star measured in light years. That will also not be great because a star should be measured in kilometers more than light years. Let's convert our distance as well. Let's convert it to kilometers. 600 light years. Light years to kilometers. 1 light year is 9.5 times 10 to the 12 kilometers. Yimmersy, check out that calculator and punch them up for me.
All right, I don't know if this is right. I have 5.7 times 10 to the power 15.
That's right. And that's kilometers, right?
Yes.
I think that's right. Yeah. Okay, let's plug this in to our small angle formula now. We're finally ready to plug and chug. I'm going to have to erase this stuff, Jordan, so let me know when you're done. I got to erase this to keep room here.
Can erase it.
So I'm going to rewrite the small angle formula, plugging in values. S is the angle, 1.4 times 10 to the minus 5 degrees, times the distance, 5.7 times 10 to the 15 kilometers, times 2 times pi over 360 degrees. Yimmersy, we're going to punch this in one clean shot. You ready to follow along with me? Let's do it. 1.4 exp negative key 5 times 5.7 exp 15 times 2 times, all you have to do to hit pi, Yimmersy, is just hit exp and then divide by 360 equals. Do you have what I have?
Yes.
All right. Help me put that into scientific notation. It's bigger than a million. Round it and put it in scientific notation.
It'll be 1.4 times 10 to the power of 9.
Very good. Units?
Degrees.
No, because degrees cancel on the top and on the bottom. What units are left?
Kilometers.
Kilometers.
That's right. And that makes sense because we're measuring the diameter of a star. It should be a unit of length. Box it. Now, we're not done with the problem. We've only earned 4 out of 5 points. To get the fifth point, we have to compare this to the sun and to 1 AU. Now compare in this class means one thing only: take the ratio. And we're going to do that in a second. Guys, hold on a second. Sorry, National Grid is out there. I hope they're not going to cut my power or something. That would be bad. Okay, guys, we have to take the ratio. Let me show you how to set that up, okay? I need to erase up here because I need some board space for this. So we're going to compare to the diameter of the sun, and we're going to compare to 1 AU. Compare means take the ratio. We can either divide the small guy by the big guy, or we could do the big guy by the small guy. It's kind of a matter of taste. In this case, I know that the diameter of Betelgeuse is much bigger than the sun. So I'm going to take the ratio of the size of Betelgeuse to the size of the sun. And when I do that, the size of Betelgeuse is 1.4 billion kilometers. Remember, the diameter of the sun is 1.4 million kilometers. Take that ratio. What do you get?
Dividing.
Pardon?
Oh no, I was talking to myself.
1,000.
What is the meaning of the 1,000?
The distance between.
Kilometers.
Not exactly. What are the units of 1,000? I need to hide the trolls here.
Kilometers.
No, because kilometers cancel with kilometers. So what does that 1,000 mean? Yimmersi, maybe we ought to make this easier, okay? Suppose you and I have a cookie baking contest, and we each bake some chocolate chip cookies. And let's say that I bake 10 cookies, and let's say that you bake 5 cookies, and that someone wants to compare our cookies. If I divide 10 cookies by 5 cookies, what do I get?
2.
What is the meaning of 2? It doesn't mean I have 2 cookies more than you, does it?
No.
What does the 2 mean?
It's just the average.
No, it's not the average. The average would be 7.5 cookies. What does it mean that 10 cookies divided by 5 cookies is 2? It means, Yimmersi, that I have 2 times more cookies than you. I have double the cookies that you have. It's a ratio. It's unitless. So what does the 1,000 mean? By analogy. Am I losing you here, or?
No, it's the ratio of the sizes of both the Betelgeuse and sun.
You are correct, but how do I say that less robotically? What's an organic way to think about the 1,000? Jordan, feel free to chime in here if you understand what I'm saying. All right, forget it. Look, it means 1,000 times bigger than the sun. Getting a ratio of 1,000 means Betelgeuse is 1,000 times bigger than the sun. It's so much bigger than the sun that it's actually bigger than 1 AU. Let's compare. The size of Betelgeuse compared to 1 AU would be 1.4 billion kilometers over 150 million kilometers. What do you guys get when you do that ratio?
So it'll be 9.3.
So roughly 9 what?
Times
9 times bigger than 1 AU. Or basically, Betelgeuse is 9 astronomical units in diameter. Now, Jupiter's orbit is 5 AU from the sun. If you put Betelgeuse where the sun was, it would swallow up the planets Mercury, Venus, Earth, Mars, the asteroid belt, and Jupiter. It's pretty intense. All right, that concludes homework number 1. It is now time for lecture, but do you guys want to take a little 10 to 15 minute break before we get into it? Just to kind of refresh your browser? You like that, Yimmersy?
Sure.
You like that, Jordan?
Yeah.
I mean, I don't know if you care or not.
Man, don't mind.
So I'm going to pause the recording for a second, and we are going to resume at 12:15. Okay? Give yourself a little pause, get a drink of water or something, just relax. 12:15, we start again. Okay, welcome back. Had to make a snack and eat a snack. I've got some thoughts going forward about what we might do. Every class kind of has its own psychology and perspective. And before I launch into this lecture, I want to get some opinions from the class here. Thank you. There are 2 different ways we can go about this. The lecture that I'm going to give to you today is on the local nighttime sky and stellar coordinates. Now, just to throw this out there as a thought, I do have these already recorded because I did these lectures for Summer 1. So I can give you the link and you could watch YouTube. It depends on whether you want more participation or less participation and more watching. Clearly, a majority of people in the class would prefer to just kind of watch the show from the comfort of their room and maybe be in the shadows a little bit more. That's fine. Yimmersy and Jordan, I'm interacting with you. That's fine too. I don't know if you guys have an opinion about that. If you'd rather do it live and then, you know, call on you a little bit more, or if you would rather, another model we could do is I can give you the link to the lecture that I've already done and then we could work on the lab together. I'm just throwing out different ideas. I don't know what you guys think about that. It's more or less the same to me, but what, Yimmersi and Jordan?
It doesn't matter to me.
It doesn't matter to you?
Same.
Well, I think there's pros and cons to both, okay? And I think we should weigh them out before we make a decision. And I don't want to make this decision alone. I want you guys to have a buy-in. So I kind of figured it might not matter to you. So one thing that I'm thinking about is, if I'm going to spend the time writing out the notes that I've already written out and you guys can watch it and do it, that's a little bit of a waste of my time when it's about the same to you. The advantage of watching the pre-recorded lectures is you can pause them if you need to do something, you can pause it and get back to it. The scary thing is if you don't get back to it, you might not get back to it, you know. The only negative side I can see to it is it's less us, you know, getting direct feedback from each other. Now, I'm always available for emails and comments or whatever. I imagine that what would happen, I've only done this live because that's what I know live from teaching. I haven't really done a lot of online courses before. So I want to make sure that you guys get the content in the way that you like to get it and that it works for the whole class. There's a part of me that thinks, wow, I'm about to do you know, a 2.5-hour lecture that I've already done, and I can just send you the link and you can watch it. So why would I do that again? The other part is maybe you guys want me to do it just for you. I don't know, you know, so what do you guys, what are your thoughts about this? I'm going to assume that there are some non-video participants here, Devon, Brendan, Harrison, and Evan. If you guys are watching with the video off in the shadows, you probably prefer to just kind of watch it pre-recorded. That's what I'm guessing. If we did do it that way, I would probably do the lab. Let's see. See, the lecture today, the lab depends on the lecture. I don't know. What do you guys think? Jordan, Yimmersi, tell me.
So I would say, so you don't have to like repeat over this thing, since we are like just tool that we are interacting, just like watch the pre-record and go through the lab.
Yeah, I'm thinking that too. So one thing we could do is we could do the lab sooner and you could watch the lecture afterwards. I don't know. Why don't we do today?
So imagine if,
oh, sorry, someone else have a thought?
I was going to say, I'd imagine if the lab, if we need information from the lecture to do the lab, we'd all have to watch that first, even if we watch it on our own time.
Yeah, well, in reality, we can kind of do the in theory, you'd want the lecture first before the lab. But what I've discovered is sometimes you can just kind of do the lab anyways and get it done and watch the lecture afterwards. Why don't we try it? I've got an idea. Today, we're already doing it live. So why don't we finish today's lecture live, and then we'll do the lab the way we did the first class, okay? And then on Tuesday, we'll try it the other way. On Tuesday, let's say we will always do the office hours live for now. I actually have the office hours pre-recorded too. So why don't we continue today live? I'll do the lecture live with you guys. You'll watch it, and then we'll do the lab, just like we did that time. And then maybe on Tuesday, we'll try it the other way around, where I send you the link to the pre-recorded homeworks, lectures, and labs, and you try it that way. And then on Thursday, we meet up again, and we decide how we liked it. Does that sound like a good plan? That's kind of scientific of us, right? We'll try it both ways.
Sounds good to me.
Sounds good to Devon. Yimmersi, Jordan, I want to get everyone's opinion here. I really care about what you guys think.
I'm okay with it.
You're okay with it?
I'm fine with it.
Okay, but if you have a preference, you let me know, because I don't know. I don't know what's better because I haven't done this many times, okay? So let's continue live today. On Tuesday, we'll try the pre-recorded method, and we'll see if there's a difference or see which one you like better. That's our plan, okay? All right. So let's get into some notes here. I want to give you guys notes on the local sky and on celestial coordinates. So there's going to be quite a bit of note-taking and quite a bit of definitioning going on here so that we can have an intelligent talk about the nighttime sky. Hold on, I lost my marker. Okay, today's lecture is on Earth's orbit and the nighttime sky. So when we look at stars and we see them rotate, they depend, they depend upon the spin of Earth, okay? So you're here and you're on a spinning Earth, and Earth has an axis spin. The axis spin gives rise to a day, which, as you know, is 24 hours. The Earth also has an orbital period as it goes around the sun, and 1 year is 365 days. So those are some conversion factors associated with the spin and the orbit of Earth. Let me call up a slide so I can show you something here. If you look oh boy, here we go. Bear with me while I get the right picture up here. I think it's around slide 14 or 13, function F512. As seen from above, Earth is orbiting the sun counterclockwise, and it's also spinning on its axis counterclockwise, if we look from above. So right now I'm pointing the Earth towards the camera. As seen from the North Pole, the Earth has a wait, let me make sure I'm getting this right. Yeah, a counterclockwise spin. So it's spinning like this, as seen from above. That's kind of important because it turns out that we use the orientation of Earth to define north, south, east, and west in space. From now on, anything that's in the direction of Earth's North Pole is north in space. Anything in the direction of the South Pole is south in space. Now, east and west are a little bit funky. Right now, I've got the United States staring at you guys, okay? This is the East Coast, and that's the West Coast. If I spin by half a day, now east is pointing in the other direction. But if you continuously spin, I want you guys to think about this. As Earth spins, it spins in the direction of Rhode Island, and it spins away from the West Coast of the United States. So there's this funny concept in astronomy that normally would sound weird, but it makes sense in astronomy. Counterclockwise in space is equal to east. It's defined as east. So we define east in space as spinning counterclockwise. That might sound pretty funny to you your first time around, but the more you meditate on it, the more good sense it makes. Now, as Earth orbits the sun, there's a couple of key points in its orbit. Let's take a look at them in a picture form here. You guys already know about astronomical units because you studied them last time. You'll notice that Earth has a closest and farthest approach to the sun. The closest approach is called perihelion. This is, by the way, because Earth's orbit is not a perfect circle. You'll discover this in your next lecture. The orbit of Earth is technically an ellipse, but we'll get into that later. This is the closest approach to the sun, perihelion. That's the farthest distance from the sun. It's called aphelion. Those are some fancy vocab terms we should write down. Perihelion is closest to the sun in orbit. And aphelion is farthest from the sun in orbit, okay? And every planet has a perihelion and an aphelion. Now, next up, we're going to take a look at the orbit of Earth. And I want to define a couple of new vocabulary terms for you guys. take a look at this very excellent picture. By the way, I want to remind you guys that all of our PowerPoints are available on, they're available on Blackboard if you ever want to look at these slides yourself. This slide shows us the orbit of Earth as a dark blue circle. And there's a name, we actually have a special vocabulary term to describe the orbit of Earth. It's called the ecliptic. And this is a big vocabulary word, so let's write this down. There's actually two different definitions of it. So the ecliptic, this is going to be definition number 1, could be considered to be the path of Earth around the sun. And that's just a basic concept. If you imagine the path of Earth around the sun as a quasi-circle, it's called the ecliptic. But I can also define something called the ecliptic plane. The ecliptic plane is a two-dimensional surface that's traced out by the ecliptic. A 2D surface made by the ecliptic. Let me just show you what I mean by that. In my slideshow here, the ecliptic is the dark blue circle. The ecliptic plane is the light blue tabletop here, okay? I want you guys to notice that Earth's tilt axis is tilted 23.5 degrees with respect to the ecliptic plane. We'll come back to that in a moment. There's also another definition of the ecliptic. It's the same thing, but it's seen in a different way. What if I oriented myself relative to the Earth so that North Pole was pointed up? The ecliptic now no longer becomes the path of the Earth around the sun, but the green circle can be thought of as the path of the sun against the background stars. So it's the path of the sun on the sky over the course of 1 year. This is a slightly more weird definition of the ecliptic. This is the ecliptic definition number 2. It's the path of the sun against the background stars. Now, I don't know if you guys remember this. This sounds kind of familiar. The path of the sun against the background stars sounds a lot like astrology, because if you look along the ecliptic, you find the constellations of the zodiac. The ecliptic is the zodiac, and the zodiac is the ecliptic. The zodiac, of course, are those signs like Capricorn, Taurus, Gemini. Let me show you one other picture as well. One of the reasons why it's so important to have the term ecliptic in your back pocket is that the orbits of the planets are pretty closely aligned to the orbit of the ecliptic. I want to type in inclinations of the planets into Google. And if you look at my image search here, you guys will notice that the planets, they basically orbit to within 1 or 2 degrees of the ecliptic, with the exception of Pluto, who's weird, and Mercury, who's weird. Most of the planets are kind of like 1 or 2 degrees off from the ecliptic. So it's not a perfect alignment, but it's pretty damn close. We use the Earth and the Sun ecliptic line as our basis for the disk of the solar system. Because the planets are so close to being in a perfect disk, take one more note about the ecliptic plane. The ecliptic plane is basically the disk of the solar system. All right. Let's take a look at the axis tilt of Earth. That's another vocab term we want to consider. The Earth is tilted by 23.5 degrees. Its axis is tilted 23.5 degrees with respect to the ecliptic. This is important. So Earth's axis tilt famously is 23.5 degrees. Sorry, oops. With respect to the ecliptic plane. Actually, it's basically, this is why your globe is tilted like this. They're showing you the axis tilt with respect to the disk of the solar system. Because the Earth is tilted on its axis, it orbits the sun in a fashion, this is a little difficult to put into words, but look at this picture. You can see that as Earth spins around the sun, that axis tilt kind of keeps the same orientation in space. In other words, if it's tilted like this, it's really hard for me to do this with such a small window from my field of view. But as Earth is orbiting around the sun, the axis tilt kind of keeps pointing up in the same direction there. And that means that the Earth makes these sort of geometrical alignments with the sun at different times of the year. The geometrical alignments are known as the equinoxes and the solstices. We have the spring equinox. During the summer solstice, the tilt points towards the sun. During the fall equinox, the axis tilt is perpendicular to the sun. During the winter solstice, the North Pole points away from the sun. Let's take a note on this as well, because I think this is important. There are 4 key points in Earth's orbit that are made by the axis tilt. It is the spring equinox, which occurs around March 21st. The summer solstice occurs around June 21st. The fall equinox occurs around September 21st. And the winter solstice is around December 21st. Guys, I want you to pause on that for just 1 second. Give me one. Terrifically sorry about that, guys. Let me get back to it here. Okay. So we just learned a little bit about the orbit of Earth and some key alignments. We learned about the 23.5 degree axis tilt. It's now time for us to kind of learn some basics about the nighttime sky and a few simple things about stellar coordinates. So I'm going to erase here. And in today's lab, we're going to be using this thing called the celestial sphere. This is sort of what the remainder of our lecture is about. It's a model of the nighttime sky in which we imagine all of the stars are stuck to a crystalline sphere, okay? And we imagine that even though obviously the stars lie at a variety of different distances with respect to us, we're going to imagine that they're all stuck to a crystalline sphere, because even though it's not true, it will help us understand how the sky rotates overhead when the Earth spins. So the celestial sphere was an idea that we borrowed from Greek philosophers. They actually believed that the stars were fixed to a crystalline sphere which rotated overhead. And while that might not be true philosophically, it's an interesting idea that helps us model the sky as a dome that is rotating overhead. So let me put that into some lecture concepts for y'all. Introducing a concept known as the celestial sphere. Oops, sorry, this is a touch screen and I almost did something bad. The celestial sphere is a useful lie. The celestial sphere is a sphere of infinite radius on which stars, planets, sun, and moon seem to rotate. Jordan, can you read this? This is a little small. Are you able to read these words here?
Yeah.
Okay, good. Before I give you any more definitions, I'd like to just show you a picture of the celestial sphere. Excuse me. Whew. Okay. There's 3 points of interest that I'd like to point out. There's a point where we project the North Pole onto the celestial sphere. That is known as the North Celestial Pole. We can project the South Pole onto the sphere. That's the South Celestial Pole. And if we extend the Earth's equator, that's the celestial equator. Those will now be some new vocabulary terms. So some key points on the celestial sphere are the North Celestial Pole, that's the projection of the North Pole onto the sky. There is the celestial equator. That's the projection of the equator onto the sky. And there is, of course, the South Celestial Pole, which, if you're a reasonable person, doesn't need a definition because it's the same idea. I sometimes abbreviate them NCP, CE, and SCP. Those are just some quick and dirty abbreviations when we're drawing diagrams. You'll see me use that sometime. Hey, class, there's a special object that resides at the North Celestial Pole. Take a guess what it is. I'm guessing you might have heard about it before. No?
North Star?
Sorry? I'm sorry. I thought I heard something, but oops. Where's my video settings? Video settings. Okay. Jordan, did you say something?
No, I said North Star.
The North Star. Yes. Do you know the name of the North Star? It's
Oh,
okay if you don't.
I don't remember. I actually studied this last year. I just don't remember the stuff that I learned last year.
Oh, okay. It's called Polaris. You can see it here. Polaris is the tail star. Function F5. It's the tail star and the Little Dipper. The Little Dipper is actually a very difficult constellation to find, but if you guys go out tonight, you should be able to find the Big Dipper in your sky. The Big Dipper is part of the constellation Ursa Major. If you follow the front two stars of the Big Dipper, they're called the pointer stars, and they actually point more or less up towards Polaris. You'll be able to see the North Star in your sky. It's not super bright. It's just a medium brightness star. The rest of the stars in the Little Dipper are a little bit difficult to see. So I would say you can see Polaris. You can't see these stars. They're too dim, unless you're in a very dark sky. You can see these two stars. So that constellation will be hard to make out, but you should be able to see the Big Dipper. I challenge you, next time you're outside at night, find the Big Dipper and see if you can use the pointer stars to find Polaris. You'd be taking your first step into a much larger world if you did that. Okay, I want to tell you something about the celestial sphere that's not obvious. And to do that, I want to use this diagram here. You can always see exactly 1/2 of the celestial sphere in your local sky. And I want to explain what I mean by that. Let's say you're a little dude standing on Earth, and you're standing in such a way that your head is pointed towards this yellow arrow. You might tend to think that your little dude is just surrounded by a little dude sky over here. And that's because you're little in comparison to the Earth, and you imagine your sky as being small around you. But actually, the entire sky that you can see encapsulates all of this green area. And that's because the Earth is really, really tiny in comparison to the celestial sphere. In essence, what it means is it means that there's no difference between the line that go from your feet to the horizon, and there's no difference between that and a line that goes to the center of the Earth. This picture makes it look like there's a difference because it shows the Earth is artificially big in comparison. But your sky, your local sky, is everything that you see in green. That's sort of important because it means that you're always seeing 1/2 of the celestial sphere, provided you ignore buildings and trees that block your view. So if you're in a desert, or if you're in a very flat field, or if you're at sea where there's no obstructions, you can see 1/2 of the celestial sphere. Let's take this as a note, because that's not necessarily obvious. You always see 1/2 of the celestial sphere in your local sky. Let me know when you got that, Jordan. All right. Cool. So let's make a little drawing of our local sky. I did provide you with this in our handout, but this picture is so important for the understanding of our class that I think it's a very good idea for us to all take a second to draw it out together. So Jordan, I noticed you had a little ruler. Yimmersy, you can use the edge of your calculator as a flat edge until you get a ruler. Let's leave ourselves some headroom. We're gonna make a 3D view. And this is a buzzword. In astronomy, it's called the local sky. It's a concept. I'm going to leave myself a lot of room at the top. I'm going to make a line that's about, on my page, it's going to be 60 centimeters. You might want to make it, let's see, where's my ruler here? Jordan, you might want to make your line maybe 10 centimeters or 8 centimeters on your page. Find the midpoint and mark it with a dot. And if you can do a line half that length, that'll kind of tell you where to put the top of the dome. And then just kind of make the best freehand dome that you can. That's about as good as I can do. Honestly, I've done better than that before. I'm not too impressed with this 30 centimeters. I'm going to try my dome one more time. One trick you can use, Jordan, since you actually have a ruler, is you can mark out a few different dots at 30 centimeters, and that'll or at half your distance there. Oh, no wonder why my dome didn't look right. I was too high. So I'm going to kind of connect the dots. Sorry, did you say something?
I also got this.
Oh, fuck yeah. That's what I'm talking about. You got yourself a protractor? By the way, that's a great tool. I strongly recommend for this course, you can get them at CVS for like a few bucks. That's a protractor. And another tool that's nice to have, Jordan, that's not too expensive. You can get it at Job Lot or whatever.
I have one laying around somewhere in my room.
That's okay. We won't need it today. Well, they're always helpful to have around, but I would say, Jordan, your trifecta of stuff to have for this class: ruler, protractor, compass, and of course your Casio.
Yeah.
We can do anything with these tools. Honestly, I was never much of an art guy. Like, I can't really draw fun things, although I wish I could, but I find that the aspect of drawing diagrams is one of my funnest, enjoyable parts of astronomy, is try to make the pictures and understand them. Anyways, I want you guys to put a dash just above and below the center dot. And what we're going to do is we're going to make the ground by making an oval that kind of connects the two center dots. This oval represents the ground, of course. Let's put an observer dude standing in the middle of the field. There's my observer. And I'll even shade in the grass. Actually, I've got multicolors here, so what do you say I really jazz this thing up? And I'll shade in some grass. Now, one thing that's not obvious to you the first time around is that it's very important that you choose your cardinal directions: north, south, east, and west. I tend to always do them in the same way so that I'm familiar with my diagram. As a right-handed person, I always want to put north on the right and south on the left. That makes east towards the observer, towards the board, and west away from the plane of the board. I am now going to do something called the fundamental positions of your local sky. Think of them as new vocabulary terms that we can use to describe stars as they rise or set. Let's begin by drawing a line through the head of my observer that cuts through the center of the sky. This is Z. I abbreviated as Z, and it's called your zenith. The zenith is the point overhead. The next thing I'm going to do is I'm going to describe the horizon as this ring that I made on the board here. So this ring is called the horizon ring. I'm just going to abbreviate it as the horizon. It's a 360-degree ring at the base of your local sky. Next up, a term to describe the arc that runs north to south through my zenith. This arc is called your meridian. That's another new vocabulary term for you. The meridian is an arc that rises due north, reaches the zenith, and sets due south. If I am an observer in the northern hemisphere, as Rhode Islanders are, I should be able to see Polaris on my sky, and that means I can see the North Celestial Pole on my sky. Let's label that by making a line that goes from the foot of the observer about halfway up the sky. I'm going to label that North Celestial Pole. And because, Jordan, we know that Polaris is there, I'll put a little star up there, and I'll remind myself that that's where Polaris is located. So the North Celestial Pole is another fundamental position. And lastly, I can also put the celestial equator on this diagram. Sorry, I'm running out of board here. Sorry, that's not well written, but it says celestial equator. My handwriting gets bad when it's down here at the bottom. Let's see how we're going to draw in our celestial equator. I want to take you back to the official slide. Notice the celestial equator is a horseshoe-like ring that goes from east to west and is perpendicular to your North Celestial Pole. Good. Oh, yeah, okay. So this really requires some good art skills. I don't have those good art skills. I'm going to do the best I can. Maybe you guys can do better. It should stay perpendicular. So that's probably where it should meet. And it's got to go from east to west. That's about the best that I can do. It's not too good, but whatever. So that ring, of course, is my celestial equator, CE. I think, you know, we had a little Bob Ross moment here where we all did a drawing together. I think that's important. To draw this out really helps you to understand the parts of your local sky. Jordan and Yemercy, let me know when you're done with a thumbs up, and I'll, all right. Jordan, you still working? Okay. Okay, cool. I'm going to erase this. Class, if we do end up doing the pre-recorded video, you're going to see me doing basically in the pre-recorded video, everything that I'm doing now, I will have done in the video. And can I make a suggestion? It's very important that the same way that you guys are copying notes now, you'll want to take notes down, okay? The only thing I'm worried about with the pre-recorded video is if you guys have a question, you can normally shout it out during class. On the other hand, what you would do during a pre-recorded video is you could pause it and send me an email, because I'll be around here to answer that stuff. Or we could have a one-on-one Zoom, whatever you want to do. I'm not sure if it's good. I'm a little scared because I've never tried doing this before. I'm used to like I'm used to steering the school bus live, you know, so I don't know what it's like if I put you on the bus and let you go. But I know some teachers do this, so you may have already had this experience. I just have not. So we're going to try it out on Tuesday, but the only point I'm trying to make is I believe that for understanding and learning, the act of writing stuff down helps you to learn and understand it. That's what I'm saying. Okay, next up, class, we're going to learn about some coordinate systems. And believe it or not, this is going to take up the majority of the rest of our day. Now that you know what your local sky is, you've got to talk about how stars can rise and set on your local sky. And it turns out it's kind of difficult to do that without some fancy vocabulary words. I just want to show you a picture of where we're going. I want to show you what it looks like when stars rotate through your nighttime sky. So first of all, if you go out at night, right, and you point a camera up at Polaris, and let's say you put your camera on a tripod and you do a long exposure photograph, you would discover that over the course of the night, as Earth spins, stars all seem to rotate and orbit around Polaris. Notice that Polaris itself is actually doing a teeny bit of a rotation, but the stars are all kind of circling around Polaris as Earth spins. They call these tracks, these lame star tracks, they call them diurnal circles or diurnal cycles. They're star tracks. And there are some stars that are so close to Polaris, you'll notice that they never actually set below your horizon. Those stars are called circumpolar stars. Not every star in this diagram is circumpolar. This star is circumpolar because it does not set. This star is not circumpolar because it does set. Let's take those as quick notes right here. So star tracks, the tracks that stars make in the sky, are called diurnal circles. Or diurnal cycles might be another way to put it too. Diurnal means twice daily or something like that. And there are also circumpolar stars. These stars never rise or set. They're usually very close to Polaris. What stars are circumpolar will depend a teensy bit on where you are on Earth, which is why we're going to have to start off with reviews of latitudes and longitudes. So I want to show you guys a picture here. Oops, sorry. This is the picture I want to show you, slide 79. Just meditate on this with me for a moment. If you could see the entire sky rotating from Rhode Island's latitude, this is what the stars look like in your own local sky as they rotate overhead. The stars rise in the east somewhere. They stay along parallel tracks. Now, do you see this line up here, the white line? The white line is your meridian. So when a star reaches its highest point in the sky, it crosses the meridian, and then it sinks back down and it sets in the west. You know, the entire rotating sky is kind of like a clock. And if the entire rotating sky is like a big clock, the meridian represents the 12 o'clock hand, the highest point that the star will reach in the sky before it sinks back down and sets in the west. I'd also like to point out that this angle that the star tracks make, this is sort of similar to what it would look like in Rhode Island. But the tracks of the stars change depending upon where you are on Earth in a not too tricky way, but a slightly tricky way. Like, for instance, if you were to go to the North Pole of Earth, the tracks that stars make would actually be kind of parallel to the horizon. They'd spin around because Polaris would be over your head. On the other hand, if you were to go to the equator, you'd see something different. Do I have a pic? Wow, I didn't include the equator. What a dummy I am. If you were to stand on the equator, instead of star tracks being circles like this, they would move perpendicular to your meridian. That's probably not very helpful to you guys. Okay. In any case, if we want to describe the motions of stars through our sky, we're going to need to review 3 types of coordinates. And I'm going to give you a little top-down structure of where we're going here. Obviously, if I asked you to describe where the North Star was in your sky, and you said, hey, it's just above my roof to the left of the little pine cone on the tree over there. Do you see that? Well, that's not a good way for us to talk to each other because I don't necessarily have the same pine cones in my yard that you do in your yard. We need to have a discussion relative to the horizon in particular. Now, the 3 coordinate systems we're going to review are something called geographical coordinates. These are for the Earth. We'll have a set of coordinates for the stars called the horizon system. Those are used to describe stars that are in your local sky. And then last but not least, we will build up towards the equatorial system. The equatorial system is a set of coordinates that we use for the global sky. And it's going to take a little while to go through these because honestly, I could just give you the definitions and then say we're done. But I know from personal experience that will not be enough to teach them to you. I'll give you the definitions and then we will practice them. All right, let's start with geographical coordinates. I'm guessing you might have heard about these before. They use 2 angles. One of the angles is called latitude. The other angle is called longitude. Let's define them and then see how they work. Latitude is defined as the degrees of a person or thing. The degrees measured north or south of the equator. So in other words, the equator here on Earth is defined as 0 degrees longitude. And as you go up or down, you're measuring degrees above there. Sometimes people call them parallels because lines of latitude are all parallel to each other. I don't know if you can see on the globe, but if you look over here, 0 degrees is on the equator, but if I go up into the Atlantic Ocean here, that's 15 degrees north, 30 degrees north, and so forth and so on, all the way up to the North Pole. Now, longitude is different because longitude works like slices. If you've ever eaten a tangerine slices that cut through the Earth. And they measure east to west. Now, unlike latitude, there's no good line of longitude that's a natural starting point. So human beings had to decide what their starting point for longitude was going to be. And a bunch of astronomy-minded people got together and they decided that the 0th line of longitude, which is known as the prime meridian, the prime meridian of longitude would run through the front door of the Royal Greenwich Observatory in England, which is pictured here. And the Royal Greenwich Observatory is just outside of London. So here's a picture of the prime meridian running through the front door of the Royal Greenwich Observatory in England. Now, if you travel to the Royal Greenwich Observatory, you can actually stand astride this line, okay? And you can take out your iPhone or whatever, and you can take a little selfie, and you can take a selfie of yourself standing with one foot in the Western Hemisphere and one foot in the Eastern Hemisphere. So that's kind of cool. In fact, some of my former students have visited the Greenwich Observatory after taking my class, and they went to the gift shop and they brought me my own prime meridian pencil from the gift shop. This is now a treasured item on my cart, the prime meridian pencil. So, you know, I probably won't ever let you borrow this because it's special to me. Feel free to bring me your own gifts if you visit the Royal Greenwich Observatory in the future. Okay, longitude then is defined as your degrees measured east or west of the prime meridian. As an example, in our own fair city of Providence, Rhode Island, we have a latitude of 42 degrees north. We have a longitude of 71 degrees west of England. Now, you guys remember me telling you that your compass app can actually identify your coordinates to a higher degree of precision. Technically speaking, my location right now in downtown Providence, I'm at 41 degrees, 49 minutes of arc, 23 arc seconds, 71 degrees, 24 arc minutes, and 44 arc seconds. Now, Jordan, I'm guessing from your accent that you were born in a different city than Providence, Rhode Island. Is that correct?
Yes.
Where were you born? What country or city?
Oh, Spain, the Canary Islands.
The Canary Islands in Spain? Are you curious?
Yeah.
Should we look up your latitude and longitude in the Canary Islands so you'll know that for your own knowledge?
Sure.
Why not, right? I'm curious. Let's go to Google Maps and let's type in Canary Islands. Oh, it's an archipelago. Nice.
Yeah.
And they're over here. Let's see if they have the geographical coordinates. That would be, you're actually probably a little closer to the prime meridian than Rhode Islanders are, right?
Probably.
Oh, huh?
Probably.
So check this out. Your original latitude is 28 degrees north and 16 degrees west. So you're only about an hour off of the prime meridian. And the 28 degrees north, I wonder, are the Canary Islands, are they kind of desert or are they more tropical? What's the climate like there?
They're more tropical.
Okay, cool. Yeah, I think the boundaries of the tropics are usually like 23.5 north to 23.5 south, but it also varies geographically and some other factors. A lot of world deserts end up being close to 30 degrees north. and 30 degrees south. But I bet because you're surrounded by all this ocean, it gives you a lot more moisture. I don't, does it rain a lot there? Do you have monsoons or
Yeah.
something? You have monsoons, right? Yeah, monsoons are cool. So that's nice because having spent some time, I mean, I'm presuming you're in Rhode Island right now. You could be for yesterday, one of the people I was talking to was actually in California, and it didn't even occur to me because I'm used to doing this live with people in the classroom. So you're not in the Canary Islands right now, are you?
Nah.
Oh, okay, because that would be kind of funny. Anyways, being in Rhode Island and the Canary Islands, you'll have some different experiences of different latitudes on Earth, okay?
Yeah.
Okay, you guys, so we can, let's write that down for your sake. The Canary Islands, they were latitude of 28 degrees north, a longitude of 16 degrees west. Cool. So we're a little bit higher and a little bit more west than you are. What about the North Pole? Can you guys tell me what the latitude and longitude of the North Pole is? Can you guess?
So the latitude has to be 90, right?
90 degrees north.
North.
Thank you. But yes. What about the longitude? Can you do that one? What would the longitude of the North Pole be? This is trickier than it might seem at first. Maybe I should show you guys a diagram. 65. Check this out. If you're standing at the North Pole, something weird happens. Your latitude is clearly 90 degrees north, but every line of longitude on Earth actually runs through the North Pole. That means every line of longitude is the North Pole. In other words, the longitude of the North Pole is undefined because it's multi-valued, and there is no unique longitude that specifies it. In mathematics, we call such a point degenerate. A degenerate point is one which has so many values associated with it that it doesn't mean anything at all anymore. So the longitude is actually undefined at the North Pole. It turns out that this is like an idea from mathematics. Anytime you construct a coordinate system on a curved surface, you will always have 2 points which are degenerate. Now, that's not an issue for the geographical coordinates, because a latitude of 90 degrees north is a unique point on Earth. If I say, hey, Jordan, I'm at 90 degrees north, I could only be one place, and that's the North Pole. That is not true if I say, hey, I'm at a latitude of 28 degrees north, because while I could be in the Canary Islands, I could also be in Jacksonville, Florida, or El Paso, New Mexico. So there are many different places that are at a latitude of 28 north, but there's only one place that's at a latitude of 90 degrees north. So weirdly, this breaks down, but this becomes a unique point which can specify your exact location. It's kind of interesting how that works. All right, geographical coordinates. Let's do the horizon system next, and then we'll take a tea break. Now that we know where we are on Earth, we can start talking about stuff that's up on the sky. And the simplest, most intuitive coordinate system for stars on your sky is called the horizon system. The horizon system is used for describing stars that are in your local sky when you and a buddy are out at a telescope together. The angles are called altitude and azimuth. altitude is defined as your degrees above the horizon. And if I want to be really technical about it, which unfortunately I do, it's degrees above the nearest horizon. The azimuth is defined as the degrees along the horizon. It's degrees along the horizon measured clockwise from north. All right. Take a look at this picture here of the horizon system, and let's see if, oh shucks, I did not mean to do that. Here's a star, and let's say I wanted to define the altitude and azimuth of the star. I find the star in my sky, and I note what the nearest point in the horizon is. The altitude tells you the number of degrees up from the ground, whereas to get the azimuth, I start north, I swivel clockwise around in degrees until I get to the nearest point on the horizon, and that is my azimuth. Can you guys give me reasonable guesses as to what the altitude and azimuth of this star would be? Throw out some numbers that aren't crazy. Let's start with altitude. What would you say would be a reasonable number of degrees to describe that star?
45.
Yeah, maybe. I guess it's halfway up to 90, something like that. Okay. What about the azimuth? How many degrees around a full circle?
360.
How many through a half a circle? Very good.
180. That's like
And
60, I'd say.
no, because you have to measure from north, right?
Oh, okay.
So from north to east is 90, correct? You with me?
Yeah.
So this is 90. To south would be 180. So I don't know who said that. Who's talking to me right there? Because you're hidden from me.
That's me, Javon.
Javon, check it out. 90, 180. What would this be?
270.
So what would you say a reasonable number for that would be?
315.
Yeah, totally. Why not? I like it. Okay, now that you guys have that, let's try a little game, and then we'll take tea break. I want to do one more sample problem with you. I want to show you how to make a 2D view of your local sky. We're going to make a similar picture to the one we made before, but this time we're going to just make it in 2D. So I'm going to leave some headroom again. Draw a line about 60 centimeters across. And I'll see if I can't make a nice dome by putting in a few dots here. If you've got that protractor, go ahead and make use of it. There's my dome, okay? This time I'm just going to keep it 2D, so there's my observer. This will be north. This will be south. I'm going to draw the observer's zenith right away. So there's my zenith. I'm also going to draw in the north celestial pole and the projection of the Earth's equator. So the north celestial pole will be up here somewhere. There's Polaris. The celestial equator runs east to west, but I can at least show where it intersects with my meridian. I've got to make sure this is at a right angle. That looks pretty decent. And I'll make a dashed line up to here. There's my celestial equator. Now I'm going to label these 4 angles with the first 4 letters of the Greek alphabet. Stay with me here. Alpha, beta, gamma, and delta. These, it's customary to label angles in physics and mathematics with Greek letters because the Greeks love geometry. Now, one of these angles, alpha, beta, gamma, delta, represents your latitude on Earth. This might be a tough question. Can anyone tell me which of the angles is representative of your latitude? I'm sorry, Yimmersy.
Beta.
Very, very good. I did not expect you to get that so fast. How did you know that? Can you walk me through that? Was it a lucky guess or did you have a logic behind it?
I'm assuming it's the degrees north and south of the equator.
So your head is this many degrees north of the equator, right?
Yeah.
Very good. Very good. In other words, let me just draw that out one more time. If this is the Earth and the North Pole is putting this way and the equator is this way and you're a dude standing up here, the angle between your head and the equator is the same as the angle between your feet and the equator is the same as the angle between the celestial equator and your zenith. That's good, Yimmersy. You got some good 3D thinking skills. One of these angles represents the altitude of Polaris. Can you guys guess which one that is? What angle represents the altitude of Polaris?
Would it be delta?
Damn, you're good. You got a knack for this stuff, kiddo. That's right. This is the altitude of Polaris because by definition of altitude, it's your degrees up from the nearest horizon. So ... that's your degrees up from the nearest horizon. Wow, really good. Okay, let's fill in some numbers here. Let's do a 2D view for the local sky for an observer in Rhode Island, because that's what most of us are familiar with. What's the latitude for Rhode Islanders, Yimmersy?
42 degrees.
So this is 42 degrees. Now, Yimmersy, if this is a right angle from the equator to the North Pole, what should that angle be equal to?
48.
Very good. But check this out, Yimmersy. There's another 90-degree angle here between the zenith and the horizon. So if this is 48, what should delta be?
42.
All right, excellent. This is good. And what about this angle for completeness sake? This is a very important diagram.
48.
Yeah. Now, there's a lot to be learned from this, friends, but I want you to start off by learning this. These angles are unique to Rhode Island, but it's always going to be true that these 2 angles are equal and these 2 angles are equal. And that means that for any location on Earth, we've just proved a fundamental and useful result. It goes like this. The altitude of Polaris is equal to your latitude. That's a really important result. You can use it to solve many problems. Nice. All right. You guys ready for a little tea break? Just chill for a bit? I can use that. Pacing it out helps you digest the material. I will pause the recording. Let's say we'll come back at 2:10. So that's a good plan. So I'll pause. Okay, everyone, we're back. All right. Learned a little bit about the horizon system, and we're going to move on to our third coordinate system, the equatorial system. Why don't I start by telling you guys some fun stuff? I'm going to share with you a video of a telescope that I'm really into. Obviously, being an astronomer, sometimes you dream at night about your favorite telescope. And if I could really get a stocking stuffer this year for Christmas, it would be a plane wave 1 meter Dahl-Kirkham telescope. These things are real nice instruments. They only cost about $200,000. So if you have any wealthy aunts or uncles that want to donate to your local poor astronomers, keep me in mind. And these telescopes are just world-class science instruments. Look at this thing. Oh, this is a Ritchie-Chrétien style telescope. Just a beautiful instrument. There's a primary mirror here. You can attach your camera and your spectrograph to it and take all kinds of images. Let me show you a picture of the thing bopping around here. Check this out. Here's a video. Now, what's interesting is the design uses what's called an altitude azimuth mount. An altitude azimuth mount. So you can see the first coordinate system that you learned being used here. So watch me hit play on this bad boy. And oh my God, it's a pair of them. Could you imagine having 2 telescopes? What's better than 1 big telescope? 2 big telescopes. Okay, so here you go. And you can see this thing swiveling around. Here they're swiveling in azimuth, right? So when they go like this, that's swiveling in azimuth around the horizon. And then the fork arms that you see there, those can go up and down in altitude. So you can point up towards your zenith or towards the horizon. And what this means, students, is that the altitude azimuth is a great system to use when you're out at the telescope with your friends or with your Grammy, because it's just very intuitive. It's how many degrees up and how many degrees along the horizon. Very simple. So if you go to the telescope with your Grammy and you say, Grammy, could you point the telescope at Sirius? She's going to say, I don't know where Sirius is. And you could say, well, Grammy, Sirius is due east at an altitude of 50 degrees. And when she puts the telescope there, sure enough, there's Sirius. But there's a couple problems with this system. One issue is, what if Grammy's not with you in Rhode Island, but what if Grammy's in the Canary Islands, right? If you call your Grammy up in the Canary Islands and say, hey, could you point the telescope at Sirius? She's going to say, I don't know where Sirius is, Jordan. And you're going to say, well, look, that's easy. It's at an altitude of, oh, wait a minute. If I'm in Rhode Island and Sirius is 50 degrees in altitude, I don't think it's going to be the same in the Canary Islands. So in a way, what we need is we need a coordinate system that will stay fixed to the celestial sphere itself. Basically, what we need is a set of latitude and longitude for the celestial sphere. Another reason why that's good, and there's many reasons why it's good, but another reason is this. If you remember the slide that I showed you guys earlier, you'll remember that as stars rise and set, they're rising in the east and they're setting in the west, and they're constantly changing their altitude and azimuth. Now, in a modern telescope, we have powerful computers that can perform the calculations showing you the path of the stars. So normally, the computer can keep moving the fork arm in altitude and azimuth for you, but if you discover a new nebula and you'd like to name it the Yimmersee Nebula before anybody else does, you're going to need a set of coordinates that stays fixed to the sky so that everyone will know that this nebula is yours. It's the Yimmersee Nebula, and you know, they have to ask you for permission if they want to look at it or something. All right, it doesn't actually work like that. But anyways, let me introduce a new coordinate system called the equatorial system of coordinates. It's a little more weird than what you're used to here. Check this out. There are 2 angles that we use, and they have kind of funny names. We call them the RA and the DEC. RA stands for right ascension. Dec stands for declination. We're going to take notes on this in a second. And here's the star Vega. We're going to measure degrees up from the equator, just like we did with latitude. And then we're going to measure degrees. Actually, we're not going to measure it in degrees. We'll measure it in time around the circle. So before I get into this here, I need to go over a couple of simple concepts with you guys. The first is, I want you to learn something about the sky rotation. Earth spins on its axis every 24 hours, and Earth orbits in a circle, or the sky rotates in a 360-degree circle. Now, weirdly enough, if you take 360 degrees and you divide it by 24 hours, you get exactly 15 degrees per hour. That's not a coincidence. There's a reason for that. In astronomy, it turns out that 15 degrees on the sky is equal to 1 hour of sky rotation. I could also say 1 hour is equal to 15 degrees of sky rotation. This is a kind of weird conversion factor that normally wouldn't make sense. Normally, angle does not equal time. But because of the constant rotation of the Earth, for astronomy, it kind of does. It's going to turn out that some of our coordinates are better measured in hours rather than in degrees. Here's another issue. Another issue that we have to address before we get going here is that we're going to be making use of a point on the sky known as the spring equinox. And I was talking with, who was it? I was talking with Javon about that. The spring equinox actually is several different things at once. Earlier in our lecture, I defined for you guys the spring equinox as a geometrical point in Earth's orbit. And if this is the sun, the spring equinox was defined as that day when the tilt of Earth makes a perpendicular line with respect to the sun. So the spring equinox is a point in Earth's orbit. It's also a day of the year. Normally, we remember the spring equinox as March 21st. However, I should point out that because of leap years, because there's not exactly 365 days in a year, the spring equinox can drift anywhere from the 20th, 21st, 22nd, and 23rd. So the equinoxes and solstices will usually warble around year after year. I think this year it actually technically occurred on March 19th, the spring equinox. That's very rare. The spring equinox is also a point on the sky. I want to address this one in a second. And lastly, the spring equinox is also a moment in time. In other words, the spring equinox is 4 things at once. And all of these things are related to each other, but they can be confusing for a student. Let's take a look at the point on the sky interpretation. The spring equinox can be thought of as the point where the celestial equator intersects the ecliptic. Here I'm using definition 2 of the ecliptic, the path of the sun against the background stars over the course of a year. If this is a point where the ecliptic and the celestial equator meet, it's also a point that's on the sky. In fact, that point is somewhere below the constellation Pisces. And although there's nothing there for you to notice it, this empty point on the sky will rise in the east and set in the west every single day. Now, I said that there's nothing there to indicate the spring equinox, and that's mostly true. 1 day per year, a very important star will appear at the spring equinox for 1 day only. You want to guess what that star is? That star is the sun. That's where the sun's going to be on the spring equinox, on March 21st. And guess where the sun's going to be on June 21st, right up here at the foot of Gemini. The sun will be in Virgo on September 21st, and on December 21st, the sun will be in Sagittarius. This is telling us where the sun is at these various days, all right? Okay, now you're ready to learn about the equatorial system. Our third coordinate system we will use in our lab today. Equatorial coordinates. They are useful for describing objects on the global sky. In other words, these coordinates stay fixed to the celestial sphere itself. The angles are called declination and right ascension. Because that's a lot, astronomers abbreviate them as dec and RA. That's how most astronomers refer to them as, dec and RA. Now, declination is kind of the same as latitude on the sky. Right ascension is kind of like longitude, but on the sky. They've got some funky definitions. Declination is defined as the degrees of a star or something like that, measured positive or negative from the celestial equator. So it's degrees plus or minus from the celestial equator. Right ascension is measured as the hours and minutes. So hours and minutes of a star measured eastward from the spring equinox. Eastward, of course, being counterclockwise. For example, there's a famous star. It'll appear in our homeworks next class. That star is called Vega. Vega has a set of coordinates, declination and right ascension. The declination of Vega is positive 38 degrees. The right ascension is 18 hours and 35 minutes. Those are rough estimates. We could probably find a more accurate version on Wikipedia, but. All right, before we leave this behind, before we do our lab, I think it's a damn good idea for us to test this out. Because I know from experience that me giving you the definitions is one thing, but you getting it and knowing how to use it is like a totally different thing. So Jordan and Yemercy, have you got all this written down here? Yep, got okays. All right, let me clear this out and let's try some sample problems. Actually, it occurs to me that I didn't do sample problems for you with the horizon system either. So what I'm going to do is I'm going to use some of the remaining time I have to do 3 sample problems. They're going to be head scratchers a bit, but I think they're really important and they're based on your homework next time. So basically what I'm doing is I'm doing some of your homework problems in advance, but I'm using them as sample problems to drill them in. So let's test out the horizon system versus the equatorial system. And let's see when it's appropriate to use one versus the other. Question 1. Describe the location of Polaris in the Rhode Island local sky. Now, you guys may have no idea what I'm talking about, or you might be following me perfectly. Let me ask Yimmersy and Jordan, or anyone else who wants to chime in the background there. Do you know which system I should use to answer this question? Take a guess. Horizon system or equatorial system?
Equatorial.
Actually, Jordan, it's the other one. It's the horizon system.
Horizon
How did
system.
I know that? Because I'm asking you about the local sky in Rhode Island. When we're doing the local sky, we should use the horizon system. So let's write that down, Jordan. Use the horizon system. By the way, Jordan, another reason I would know it's the horizon system is Polaris does have a set of equatorial coordinates, and I'd like to show them to you real quick. Wait, hold on. Let me share screen. Jordan, Polaris has a set of equatorial coordinates, which we could look up. I vaguely know what they are, but let's just look them up quick together. Although Polaris does have a set of equatorial coordinates, let's look at it right here. It's positive 89 degrees and 15 arc minutes, and it's 2 hours and 31 minutes. These coordinates of Polaris are for everyone on Earth, right? Because they're for everyone on Earth, they're not unique to the Rhode Island local sky. If I'm asking you to describe the location of Polaris in the Rhode Island local sky, that means I want to know, like, where is it relative to 2 people standing outside at night in our own backyards. Oops, sorry, that's my bad. Jordan, what angles does the horizon system use?
Altitude and azimuth.
So that's what we need to solve this problem. Do you think you can do that, Jordan? What would the altitude of Polaris be in the Rhode Island local sky? What would the azimuth of Polaris be in your local sky? I'll call up a picture of local sky while you think about that. So,
Would it be 90?
no. Also, can I point something out, Yimmersy? I'm looking for 2 angles. So if you want to be really clear, which I know you do, you need to specify which angle you're telling me about. I'm going to use my stamp feature. Polaris is kind of bluish. Check this out, Yimmersy. Boom. Shoot. Why is it yellow, you bastard? I wanted you to be blue. Is it incapable of being blue? All right, well, whatever. There's Polaris right there, right? Now, when you say 90, remember, Yimmersi, you got this right earlier. You were actually pretty damn good
42.
when it came to the horizon system. Remember the alpha, beta, delta, gamma game that we had? You kind of crushed that, if I remember correctly.
Isn't it 42?
Which one? Maybe, Jordan. It depends which angle you give me, the altitude or the azimuth.
Altitude.
Very good. It's
The altitude.
42 degrees because we learned that the altitude of Polaris is equal to your latitude. What about the azimuth, Jordan? How do we define azimuth again?
Degree along the horizon.
Right. So, but measured from
clockwise.
north.
From north.
So this is kind of like azimuth is the same as direction. What direction do you think the North Star is in? This is kind of like what color is an orange or who's buried in Grant's tomb. What direction would the North Star be in?
North.
Yes, of course. But Jordan, what if I wanted the technical azimuth? What would the technical azimuth of north be? Remember, Jordan, we measure degrees from north clockwise. So if you're on north, how many degrees from north are you?
42.
No, 0.
Zero.
Okay, Jordan, I think maybe what we should do is label this diagram here.
Yeah.
This is 0 degrees in azimuth. This is 90 degrees in azimuth. This is 180 degrees in azimuth, okay? And this is 270. Does that make sense to you?
Okay.
Azimuth goes around in a circle from north. Now your star might be here, Jordan. It's up here in the sky, but the closest point along the horizon is that point. Do you agree that the closest point to that is that? Therefore, you are due north or 0 degrees. Let's take this down as both so that you see. So the azimuth is 0 degrees or north. Those are both equivalent way. Sometimes, students, I'll just accept a direction in place of azimuth. That's fine. Jordan Yimmersi, when you're done writing this down, I'm going to try another problem. Give me the thumbs up when you're good to go. All right. Let's try your skills on another question. Describe the path of the celestial equator in the Rhode Island local sky. Now, Yimmersi or Jordan or anyone else who wants to, what do you think we're going to use for this problem? Horizon system or the equatorial system? You're muted, Jordan. Do you know, Yimmersi? Jordan, do you know?
Horizon. Because we
Hold
want to find it out on the local sky.
Yeah, I think you said the right answer. Can you say the answer one more time? Because there was a glitch in the matrix. Shit, Jordan. I think you're freezing.
The horizon, because we are trying to find out in the. Oh, shoot. How about now?
Yes. Jordan, that's right. We're going to use the horizon system. You glitched out on me again, but I heard you say we're going to use the horizon system because it's in the local sky. Is that what you said?
Yeah.
Awesome. Let's write it down. Jordan, there's a new twist and a new plot twist here that you might not be anticipating. Let me show you my local sky once more. Do you agree with me, Jordan, that this line here is your celestial equator?
Yeah.
Here's the thing. Normally, altitude and azimuth, they describe a single point on your sky. But this isn't a point. This is an arc. So it's going to be more complex to describe. Write that down with me. Also, it's an arc. It's not a point. And when we describe an arc, we need a bare minimum of 3 points to describe its trajectory. And you ever see Jordan, each of those points will have its own altitude and azimuth, meaning a total of 6 coordinate numbers. I refer to those 3 points in my head as the rise, the reach, and the set. Let's write this down. We're going to have a rise, a reach point, and a set point. And for each of these points, there is going to be an altitude and an azimuth. This is your first time doing an arc, so I'm going to help you. Let me show you where the rise, the reach, and the set are. I will use the annotate feature here. I'll use blue dots. Okay, so check me out. In my mind, this blue dot is the rise, because it usually stars rise in the east. The reach is usually the point that's the highest in the sky. So that's my reach point. And there's my set point. Now, I can give you the answers, but I think it would be way better for your brains if you try to figure out what they are yourself. So Jordan, let's start with you because you and I have been talking. Jordan, Yimmersi, I'll make you do the next one. Jordan, do you think you could describe the altitude and the azimuth of this point?
Altitude will it be 42 and
Hold on.
I forgot.
Jordan, just talk
Yeah.
with me here. This point has an altitude and an azimuth. Let's start with altitude. What would the altitude of this point be here where my cross is?
0.
Exactly, because it's on the horizon.
Yeah.
So the altitude is 0 degrees. Now, how do we define the azimuth again, Jordan? Just read the definition to me.
Is the degree along the horizon, clockwise from north.
From north. In other words, the blue arrow, degrees along the horizon measured clockwise from north. Can you tell me, based on this blue arrow, what the azimuth is?
Oh, I really forgot about that.
90.
Very good, Yimmersi. That's okay. We phoned a friend. See, Jordan, from the north, am I stressing you out? Or...
No.
Listen, Jordan, there's a reason why they call it astrophysics, because it's not fucking easy or obvious, okay? There's a reason why you have to pay some jerk like me $500 to learn this stuff. You're not just born knowing it, okay? So this is a struggle. The struggle is real, but the struggle is noble and it's good, okay? So keep in mind, I'm asking you these questions because I know that you're going to have to think and it's going to be tricky. But Yimmersi hooked us up here. She says, look, guys, from north to east, it's 90 degrees. And I want you to add one more thing here. So we could describe it with either one of those two things. We could say 90 degrees, or we could say east, same thing. And sometimes people have a statement, when you're on the, if you're on the horizon east, you can call that due east. Okay, so Yimmersi or Jordan, or anyone else in the background trolls who think they know what's up, here's your next point here. This is the reach. It's the highest point of the celestial equator. Can you give me the altitude and or the azimuth, and please be specific about which you're giving me?
The azimuth is 180 degrees for
Excellent.
the reach.
Yes, correct. 180 degrees, which is the same as south, right? I want to be very clear what Yimmersey just did there for anyone who realizes it. I'm going to use a different color like red for a second. Yimmersey notices that this is the closest point to the blue dot on the horizon. And Yimmersey is saying you're good at azimuths, Yimmersey, so from there to there is obviously 180 degrees. Good. Okay, but we also, Yimmersey, need to deal with the altitude, which you'll remember is the degrees from south up to here. To get an answer, you might make use of your alpha, beta, delta, gamma diagram. That could help you here.
42 degrees.
Try again. Look at the alpha, beta, gamma, delta.
48.
48.
Yes, yes. Remember, Yimmersey, you identified this angle as your latitude, so it's the opposite. Yeah, okay. Excellent. And now last, I bet you guys can clean this up quick. What's the altitude and azimuth of that point there?
Is
0 and 270.
Excellent. Whoever said that, great job. 0 degrees, and it's 270 degrees or west, which is the same as due west, okay? Notice that this was not due south because it wasn't due. It wasn't on the horizon. It was above the horizon. By the way, this is going to be one of your homework problems on Tuesday. So straight up from your homework, I'll go over it again on Tuesday, or my recorded self will go over it on Tuesday, whichever happens. All right, I got one more problem for you. Then we can hit the lab.
freaking A.
Oh, did I go too fast, George? Did I screw you up? I did.
My internet just
No,
broke
no.
down.
Tell me what you need, and I'll put it back up there. Here.
What was the last thing that you?
The last thing that I wrote. Sorry, dude. I should have asked. There was the rise. There was the reach, and there was the set. The set was 0 degrees.
And 270, right?
Yep, or west. And that's the same as due west. I try to always ask you guys if you're finished before I erase, but every now and then I forget, so.
My connection just.
Oh, yeah, that happened to me earlier too. I sympathize. I asked Cox if there was a solution to the problem, and you know what they said? Maybe you should try upgrading to the more expensive internet.
Yeah, sure that.
Honestly, I'm thinking about it though for fall. I'm thinking about shelling out a few more bucks to have. I don't know. I bet the same glitches are there, but who knows? Are you good now, Jordan?
Yep.
All right. All right, we have to do one more problem, guys. Horizon system versus equatorial system. Question 3. Describe the coordinates of the 4 key points in Earth's orbit. And what I mean by the 4 key points, and I mean coordinates like observer independent coordinates. I don't know if that's too mumbo jumbo for you guys or what. Answer 3, do you know which system we want to use here? This is not observer dependent. This will be true for any observer. Yimmersy, which system do I want?
Equatorial coordinates.
Oh, yeah. Okay, let's do this by the numbers. This is going to be trickier first time around. Let's start with the spring equinox. The spring equinox is going to require a declination and a right ascension, abbreviated DEC and RA. To do this, I think we should start, you know the picture that I like to use for this, but you guys may not like it as much? Remember that this picture is tilted by 23.5 degrees. Remember the celestial equator is the red ring. So let's start with this point right here. There's the spring equinox. Now, how do we define declination again, Yimmersy? Maybe just regurgitate it for me.
Degrees measured plus or minus from the celestial equator.
Notice that the spring equinox is on the celestial equator. So what would its declination be? Jordan's got it. Yeah, 0 degrees. Now, if I could abbreviate the definition of right ascension goes like this blue arrow that I'm about to draw here. It's the hours, not degrees, but the hours measured eastward from the spring equinox. Remember that eastward is counterclockwise as seen from north. So you start at the spring equinox and you go like this, and to go around the circle is 24 hours. What would the right ascension of this point be? You're on the spring equinox, but you're trying to measure hours from the spring equinox. So does that make any sense? What's the RA of this point?
You said you're on the spring equinox?
Yeah,
So it should be 0.
exactly. 0 hours. By the way, just because, who's chiming in there so I know how to address you? Because
Sorry,
I had,
that's me, Javon. I don't have a camera.
that's okay, Javon. There's no shame in that game. I just want to be able to know, I want to start to recognize your voice, that's all. Okay, exactly, Javon. You're crushing it. So the right ascension, but we write it as a 24-hour time. We write it as 00:00. Let's next try the summer solstice. Let's see if you can do this with less help, otherwise I'll give you hints. The summer solstice is this point here. Can any of you give me the right ascension or the declination of that point?
Would it be positive 23.5
That's
degrees?
Which one is that? The right ascension or the declination?
Declination.
Exactly. Exactly. And I like how you threw positive Yimmersy. 23.5 degrees. What about the right ascension?
Mm. 6 hours.
Awesome. Man, you are good. I think we need to sign you up for Astronomer Junior over here because look, that's a quarter turn around the globe, right? And if a quarter of 24 hours is 6 hours, that's real good. All right, this is going smooth. Okay, next we'll try the fall equinox. Let's try to pick up speed here. Declination and RA. Hit me one time.
Declination 0 degree.
0 degrees, excellent. And the right ascension?
24.
I'm sorry, Jordan?
24. 24?
Careful. Remember, Jordan, that an entire spin around the sky is 24 hours. It's 24 hours to go around the entire sky. You're going half the sky. Do you see what I'm saying?
Yeah.
So how many hours would it be to go half a turn?
12?
Exactly. And lastly, we'll do the winter solstice. The declination and the right ascension. Here's our dot.
So for the winter will be, the declination will be negative 23.5 degrees.
Yes.
And the RA will be 18 hours.
Yeah. Wow. You guys got that pretty quickly. People usually take a longer time. They struggle with that usually. So that's nice. That's very nice. Before I end class, remember that next class we're going to attempt to do the pre-recording, although I might just kind of show up at some point. I might want to just talk to you guys at some point through it. I don't know exactly how that's going to work, but I have recordings for the office hours, for lecture, and for lab. I might try just letting you run entirely on the pre-recorded thing and be available for questions or one-on-one Zoom. But let me tell you about what, now of course in our office hours, I will be explaining everything in exactly the same level of detail that I do here. I think you're gonna find it's good, but we'll find out. But can I show you guys a couple of calculator tricks? I'm particularly worried because Yimersi, you have the Casio calculator, but Jordan, you're using something on the phone, you're using something on your phone, correct? Okay, so there's a new formula that we're going to have to learn for planetary orbits, and it's called Kepler's third law, and it involves using a square key and a cube key. I don't know if you guys have done that before, because my students have a wide variety of math backgrounds. Some of you guys know calculus, other people can't even add basic numbers together. I've got to figure out who can do what. So I want to show you one last formula that's going to be in your homework next time. And I want to see kind of how you guys handle it with the sample problem. Obviously, during the lecture, I'll be explaining the formula in detail and telling you about what the formula means. But for now, I'm less interested in that. I'm just more interested in if you can find the right buttons in your calculator. So, Jordan, can I erase here? All right. I want to take a look at the orbit of a planet. So here's the sun. And a planet has an orbit which is almost a circle, but usually there's something called ellipses, okay? So here's your planet going around the sun. And our next class is going to be consumed with understanding both orbits and gravity. That's the next piece of the puzzle that you guys need. Let me introduce some terms to you. So for planetary orbits, planets have an orbital period, which we're going to use the symbol P for. P is the period of the planet. And that's going to be measured for now in years. The period of Earth is obviously 1 year, but there are other periods for other planets depending on how far from the sun they are. Now make a little line with me here. Dash, 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 dash. A is going to be the average distance between the planet and the sun. We use the letter A for historical reasons because Johannes Kepler did. A is the average distance between the planet and the sun. And most importantly, this is going to be measured in astronomical units, which you learned about last time. Last but not least, the planet has a perihelion and an aphelion point. This point here is peri. Peri is short for perihelion. And this point here is, I use APH for aphelion, okay? Oops, sorry, I want to give you all the abbreviations. Peri is perihelion in AU. Aph is the aphelion in AU. And finally, I would like to introduce a new parameter having to do with planetary orbits. Let me show you a picture of this parameter before I tell you what it is. It's called the orbital eccentricity of the planet. And there's a cute little image here. This is what I want. Check this out, guys. Planet orbits can be circular or they can be oval or eccentric. And there's a parameter which specifies how eccentric the orbit is. It's called the eccentricity. When the eccentricity is 0, the orbit is a circle. And the eccentricity can go all the way up to 0.2, 0.5, all the way up to 0.99999 forever. It can never be 1. Oh, hello there. But this is this eccentricity is 0.95. It's kind of cigar shaped. So one jokey way that I like to tell my students about it is the eccentricity E I like to think of it as the percent squishiness. It's the percent squishiness of my orbit. And famously, eccentricity has no units because it's just a percent. The domain, ooh, look at my fancy math terms. The domain of eccentricity is it can be greater than or equal to 0, but will always be less than 1. The domain. Or is it the range? I can never get those two straight. I think it's the domain. Range is for the independent variable. Domain is for the dependent variable. That's how I remember it. All right, just put all this down in your notes. I'm going to explain it next time. Think of this as me priming the pump. Okay, how are these guys all related to each other? With the following formulas. Jordan, can I erase? Yemmercy, can I erase? I can relate these things by an equation called Kepler's third law. And honestly, it's a pretty simple formula, but I want to test it out on you guys. P, the period squared, is equal to A, the average distance cubed, provided we have the right units. Period is in years, and A is in astronomical units. And do remember, this A refers to the average distance shown in the diagram above. Okay, other formulas that we need are the perihelion is A is sometimes called the semi-major axis. A is the perihelion is the average distance times 1 minus the eccentricity. And the aphelion is the semi-major axis times 1 plus the eccentricity. And in the video on Tuesday, I'm going to explain this all over again. So I'm giving it to you twice. I'm just trying two different directions of coming at it to see how it works. What I'm concerned about is because you might end up doing the homework with the video, I want to talk to you guys about your calculator buttons and make sure that you, Jordan, and you, Yimmersy, and Javon, if you're in the background, John, can you hear me? Do you have a calculator?
Yes, I have a nice bright pink FX260.
Yes, I love the bright pink one. That's awesome. You are the shit. Okay, so let me give you a sample problem showing you how these equations would be used. It's actually quite simple. Let's try Jupiter as an let's try Pluto as an example. Do you guys have all this down? Jordan, you good? All right.
I should have my own notes laying around somewhere in my room.
Oh, say that again? Oh, because you said you took this class before, or part of it?
I took the, wait, which one is this one?
This is 1020.
I'm sorry. Yeah, this is the stellar system. I took the solar system.
Who did you take it with, Jordan? Do you remember the
I don't
professor?
remember it was old, but I don't remember the name.
Was it in Lincoln or was it in Warwick?
Lincoln.
So probably Jack Owens, huh?
Owens, yeah.
Yeah, okay. All right. Well, that's interesting because now you'll get to learn it from a different professor and see, compare the differences, right?
Yeah.
Okay. Let's try this problem. What if I told you guys that Pluto has, no, actually, we're going to do Jupiter instead. Sorry, I'm going back and forth. I'm trying to decide what to do. Jupiter has an average distance of 5 AU from the sun. I think Jupiter's orbital eccentricity is wicked, wicked low. Jupiter's orbit is super circular. Let me look it up just to be sure. I bet it's like 0.2 or 0.3 or something. Orbital eccentricity. You can get this stuff right from Wikipedia. 0.05. Okay. And an eccentricity (0.05). So this is our question, okay? And the question that we're trying to address is this. If I tell you all this stuff, can you find the period of Jupiter and the perihelion and the aphelion distances? Okay? So let me take you through this by the numbers. To get the period, we're going to use Kepler's third law. P squared equals A cubed. Now, if I wanted to, I could plug the distance right into A. But because I'm kind of particular about how I do algebra, I like to solve the period first. And the problem is that you can see there's a square up here. The square is kind of in my way. Now, if y'all remember your maths, to kill a square, you apply a square root to both sides. So let's write that down next. So I'm going to solve algebraically for P. P is the square root of A cubed. And now I'm going to plug in my numbers. We have to recognize that the average distance is A, the semi-major axis of orbit. So I've got the square root of 5 AU cubed. That's how I would write it. All right. Now, let me walk you through the buttons you're going to need. Can you see the Casio? Jordan, we'll have to find yours for you. There is a square, and there is the square root in orange. But can you guys see these buttons here? In orange, that key is your cube root. And in let me try that again. That key in orange is your cube. And that key in orange is the cube root, meaning you have to hit shift first. So let's try this. Everyone start by punch. Oh, Jordan, hopefully, can you show me your dude? Hold on, I got to full screen you so I can see what's going on. Okay, Jordan, you have, keep it there. Okay, I can see you've got a cube and a cube root and a square root. They're kind of 2 keys above the 8. Do you see them all? Start at the number 8. And yeah, they're all kind of up there. But I can't resolve on your screen. Is that a cubed root or is that an arbitrary root? What's above the little notch? Is it a 3? It looks like a 3. There's a cube root there. Actually, that's a pretty damn good calculator. What calculator did you say that was again? I want to write that down.
Hyper scientific calculator.
Hyper scientific calculator. And that's for a Google phone, correct?
Yeah, but instead of a Y, it's an I.
Like H-I, hyper?
Yeah.
Okay, that's a good Google app. Because sometimes my students like you have Google phones and I have to come up with good apps. Okay, that's great because you have your cube root, your square and your square root all in an easy to locate place, right?
Yeah.
So everyone follow along with me. Yimmersi, Javon, watch my moves. Let's start with 5. 5. And to cube it, I'm going to hit Shift and then cube. So far, so good? Now watch me apply the square root. I'm going to do Shift square root. Is that what you have? Answer?
Okay.
11 years. Let's find the perihelion and the aphelion distances. We're going to use the 5 AU. Peri is 5 AU times 1 minus 0.05. Okay, let's use our parenthesis keys for this. Everyone watch how I do it and learn my moves, okay? I type 5 AU, I do times, and now I'm going to hit my open parenthesis key. 1 minus 0.05. Watch what happens when I close the parentheses. Bada boom, that does the interior of the parentheses, and then I press equal to finish the job. 4.75 AU. Or I could round it to 4.8 AU, whatever. Okay, now you guys try it with the aphelion. The aphelion is 5 AU times 1 plus 0.05. Tell me what you get.
Should be 5.25.
Nice. Good job, Javon. So how did that feel for you guys? Was that nuts or was that pretty straightforward?
Still have a little bit of issues how to do on this.
Okay, hold on a second. Did you say you were having trouble, Jordan?
Yeah.
Hey, Jordan, look at me for a second. Let's talk. Do you now see why it's important for us to all have the same calculator?
Yeah.
Are you prepared to spend $9 at Walmart and buy your... Actually, wait, Javon, where'd you get the hot pink one?
It's at Target. It was the same price.
Booyah. So Target all day, okay? Now, I can't make you do this, but I strongly encourage you to do it because then we'll all have the same calculator and the same set of instructions. Way better, right?
Yeah.
Okay. So think about that. You've got 4 days until our next meeting or virtual meeting, whatever it is. Okay, let me see your calculator. Meantime, I'll show you how to do it, okay? So punch 5.
5.
Now, show me your calculator again, because I have to try to tell you where your key is. It looks to me like your square key, ooh, push it over a little bit. Your square key is 2 keys above the 8, from what I can tell. Yeah. All right, hit that. Oh, wait, you have to, God damn it. No, you're not squaring it. You're cubing it, right? I apologize. Let me try, show me your calculator again. Your cube key is 2 keys above the 8, but you have to hit the shift key first. Where's your shift?
Is the one that says X to the 3?
Yes. But you have to hit shift before you hit that key.
Okay.
What do you see? Do you see 125?
Yeah.
All right. Now wait, you have to square root it now. So now with 125 there, show me your calculator again. I've got to tell you where your fucking square root is because I can't show it to me. I don't have a Google phone. I don't know how to call this up. Your key is, that's your cube root. Oh, sorry, that's the square root. Yeah, hit that button. Just hit it. And you should, do you see 11.2? Or 11-ish?
11.18.
Correct. All right.
All right.
Look, you get this thing from now on, okay?
Yeah.
Way better for all of us. All right, guys, let's work on our lab. Let me show you the lab that we're going to do today. We're going to do a shortened version of the Celestial Spheres lab. So if you can, it would be very helpful. Let me share a file with you guys. Do you guys see here? This one you can actually type up if you want. Oh, shucks. Hold on. Hate Blackboard. Okay, this Celestial Spheres lab, do you guys see how I gave you the docx? You guys might actually want to just type it into your docx, although I'm going to print mine out. Let me hit File, Print. Your version, guys, check out the docx version. Oh, I gave you guys the document here. And if you want, if you don't have a printer handy, you can actually open up Microsoft Word and type the answers into here and just submit the Word document. By the way, if anyone's worried about what if I don't have Microsoft Word, you have access to Microsoft Word through CCRI. If you guys, I don't know if you know this trick, but if you're on your CCRI email, do you see these 9 dots up here? You click on the 9 dots and you can launch Microsoft Word right from there. So I'm going to print mine out and photograph it, but you guys can actually type it in that way. Let's head on over to the lab room. Okay. Let me activate my Wi-Fi. Oh, it's already activated. Okay, guys. Can you see me? All right. We're going to use our celestial sphere. I'm gonna be honest with you guys. This is one of those labs where unfortunately it's just way freaking cooler to do it in person than it is to do it the way we're about to do it. And that's because in the lab room, you each get each team gets their own globe. So it's usually like a globe per every 3 or 4 people. and you kind of talk together and you get to explore the different stars. And I'm not going to say it's as much fun as riding a roller coaster, but as far as labs go, it's actually kind of fun. Today, we can't do that because these globes are quite expensive. So I'm going to use my phone to guide you around the globe, and it'll be a little wonky, but we'll make do, okay? Now, we're going to be hunting down the names of famous stars and famous constellations. So I kind of show you a screen. Up to now, I have only talked briefly about constellations, but here it might be good to kind of say some things about it. Let me just show you here. Check out this slide that I'm showing you. Constellations are not simply stick figures. Constellations actually represent areas of the sky. So while we know that Orion is, of course, these stars here, and there's a stick figure, the actual boundary of the constellation of Orion kind of follows the stick figure and traces out a square in space. So if I were to discover a new galaxy or a new nebula that was here, we would say that that galaxy is in the constellation of Orion because it's inside one of the territories. And this should be a familiar concept to you guys because the United States kind of works the same way. Every part of the United States is blocked out into states. Every part of the celestial sphere is blocked out into one of 88 constellations. Now let me orient you to our globe next. I'm going to attempt to share this to my iPhone. I hope this works this time because sometimes it doesn't. Share screen, iPhone. Let's see if we have any luck. Yes, the gods are with us. Just give it a second while it connects. Come on, baby, connect. Come on, baby, connect. Don't let me down. It says it's connecting. Shoot. That's bad. It lost it. Share screen. There we go, you bastard. Okay. Now take a look at my globe here. It's transparent, so that's going to present some challenges. I do have an envelope and a piece of paper that might be helpful. Okay, so take a look in here. Here you can see the globe. And right now, if I, hold on, I think I can use this. I'm a damn genius. Okay, here we go. Look at that. Now I can rotate the cardboard around. Okay. So here on the celestial sphere, this is the celestial equator right here. And as you know, the celestial equator is 0 degrees of declination. And the declination goes up like lines of latitude. This is +10, +20, +30, +40, all the way up. Down here would be negatives, right? This is -10, -20. The hours of right ascension are printed here. There's 0 hours of right ascension. This, it's a little bit, oh, shucks. Okay, that's kind of cool. Sorry. That's 1 hour of right ascension, right? There's 2 hours of right ascension. It's all printed backwards because you're supposed to like look through the globe and then read it from the other side the way you would the sky, but we'll just do it backwards. Now look, you can break up the minutes of right ascension. Let's go back to this one here. Up at the positive 10 degree mark, they break up the hours of right ascension into minutes. So the little tick marks that you see there, those are each 4 minutes. The big tick marks are each 20 minutes. Now, the names of the constellations are in blue. The names of the stars, like alpha rats, are printed in black. The stick figures are done with the solid blue line. And can you guys see these dotted blue lines here? Those are the boundaries of the constellations. Now, why that's important is during the course of this lab, I'll ask you to find a famous star or a famous planet or galaxy. And if you want to know what constellation it's in, you've got to make sure that you don't cross one of the boundaries of the dotted lines. So let's take a look at our first operation here. First of all, if I could ask you guys for a favor, at the top of the page, when you're going to be turning in, obviously put your name or type it if you're using the document. And I need to know that you guys are in AS1020. So put AS1020 down. That's important. Anytime you write me an email or talk to me, I'm still learning a lot of you guys. So you got to say AS1020 on everything. Okay, what we see in the first project here is these are the 10 brightest stars in the nighttime sky. And we've been given their equatorial coordinates, right ascension and declination. And our job is simple. Find the star name, find the constellation name. Our first task is a star which has an RA of 6 hours and 43 minutes and a deck of -17 degrees. So let's go hunting. This is 1 hour, 2 hours, 4 hours, and 6 hours is right here. And this is 6 hours and 43 minutes. Now, if the little guys are 4 and the big guys are 20, this is 6 hours, that's 7 hours, that's 6 hours and 40 minutes, and that tick there is 6 hours and 44 minutes. So it's going to be kind of close to this line here. Now, our declination is -17 degrees. So let's head down from 643. I might want to make use of a piece of paper here. Ah, shoot. All right. So this is 643. I'm going to drop down -10, -20, -17 is there. What's my star?
Cyrus.
Sirius is the name of the star. It's the brightest star in the sky, actually. And what is the name of the constellation?
Canis Major.
Canis Major, the big dog. All right. Next up, 737, +5. So here's 7. Oops, sorry. 7, 8, 740, 736. That's pretty close. And we're going to go, oh, sorry, we have to start at the celestial equator, though. So that's 736, during the celestial equator, we go up +5. Our star is Procyon in Canis Minor. Next up, 2040, +45. We're going to have to spin all the way around the bloody globe here. Okay. So we have to stay on the celestial equator. That's 2020, that's 2040. and we're going up positive 45, positive 10, positive 20, positive 30, positive 40, and there's positive 45. What's our star?
Deneb.
Deneb. And the constellation is, let me see if I can get that readable to you guys. It's Cygnus the Swan. That constellation, by the way, Cygnus, is sometimes called the Northern Cross. You might actually be able to find it on your sky tonight. If you look for it, it'll probably be like sideways on your sky. But Deneb is the tail of the swan. And it kind of looks like a cross. Those are the wings of the swan, and that's the tail. But this is Deneb right here. Deneb is a very bright star in your sky. I bet you could find that. Okay. 1948 and positive 9. So here's 19 hours. 1920, 1948 would be a little bit past it. And plus 9 brings us up to here. Altair is the star in Aquila the eagle. Aquila. I think it's Aquila. By the way, together, I don't remember how it works, but Deneb, the bright star Vega, and Altair make a 90-degree triangle in space called the Summer Triangle. 3 bright stars from 3 bright constellations. These 3 stars are so bright that you guys could go out tonight if the skies are clear and look up around 9 p.m. and I bet you could find the Summer Triangle. You wouldn't believe it, but when you get to know just a few basic constellations, it's like the nighttime sky is your friend. It's like an old familiar face, and it's nice to look at it. Have you ever heard of this, Yimmersi, or seen this?
I've heard of the Vega, but I haven't heard of the other one.
Triangle. Well, anyways, maybe one day you guys can visit the observatory and I'll show that to you. Next up, 513, positive 46. So let's hunt around here. We're heading back over to this side. Hold on a minute while I grapple. Just a sec. I'm trying to set up an artificer here. Whoops. 513, positive 46. So here's 5. 513 is like a quarter turn. And then we'll go up positive 46. 10, 20, 30, 46. And there's our star. It's called Capella. Capella is the brightest star in Auriga, which I think is a shepherd or something. Auriga. Next up, 513 minus 8. So same as before, we go to 5. A quarter turn is 513. Minus 8 brings us to this star. This star is actually Rigel, and Rigel's in the constellation of Orion. (1410). Actually, notice that these two are next to each other. I'm going to jump ahead, guys. We're going to do number 8 next, okay? So it's in the same neighborhood. 553 and positive 7. So there's 5. 5:53 would be almost at the 6th hour of right ascension. +7 goes up here. Oh, here's a familiar face. Betelgeuse in Orion. Let's jump around now to 1410. 14 is over here. So I'll rotate, rotate, rotate. $14.10 is about there. And +19, 1020. There's my man, Arcturus. And Arcturus is in this constellation up here. Let me show you at an angle. Let's get the star name, Arcturus. The constellation, it looks like, oh, it's getting very sunny. It looks like booties, but it's Bootes, okay? Here's how you spell that. B-O-O. The second O has an umlaut. Sweet. Bootes. (1627) and -26. 16, 20, 24, 28. We have to go down here. Hold on. Ugh. I'm in the hole. There we go. 1627 and -26. Down 10, down 20, down 6. That's Antares. Antares, which is anti-Mars. The constellation. All right, we have to be careful not to cross a dotted line here. It looks like there's a dotted line there, but if we stay below, we are still in Scorpius. Last but not least, 1836 and +39. Here's 18. 36 is about halfway. 10, 20, 39. Oh, there she is. Vega. And Vega, oops, sorry, I'm getting dim here, is in the constellation of Lyra. Lyra is a harp. Cool. Okay, guys, we're gonna do, it's 3:35. I've got a plan for us. We'll do this table, okay? And we'll do one more little fun game that I have to play, and then we'll call it, okay? So we'll just do a teensy bit more together. Now, the names of the stars are obviously printed on my globe, but I got a question for y'all. The names of the planets are not printed on the globe. Can you guess why? Why would astronomers put the stars on, but not the planets?
Is it because they move?
Yeah. In fact, Yimmersi, our English word planet comes from the Greek word planitos or something like that. And in Greek, that means the wanderer. The planets were those who wander against the sky. Now, if you want to know where the planets are, you can often look up a table called an ephemeris table. They used to print them in books, but now most people just look them up online. There's one that I like on ephemeris.com. I usually just type in Sun to Sedna, and it comes right up here. And And they're going to ask us to find the locations of the 5 classical naked eye planets. Sorry, I don't want to stop sharing because you saw it was a beast to get this phone working. Mercury through Saturn. And they have their right ascensions and their declinations here. Let's kind of jot these down in shorthand form. So for Mercury, it's 636 and positive 18. Hold on, I gotta sharpen this dude here. Or use this other one. So we're gonna do RA and we're gonna do dec here, all right? Can you guys see what I'm doing here? So 636 and positive 18 degrees. Just jot these down. Normally I put them up on the board, but I can't really do that in this format here. So for Venus, it's 421 and positive 17 degrees. For Mars, it's 0, 15, and positive 2 degrees. I'm just kind of rounding to the nearest degree. For Jupiter, it's 1942. For Saturn, it's 2008. And their declinations are positive 21 degrees and negative 20 degrees. I'm surprised there's so many degrees apart. The other, oh, I'm sorry, whoa. My mouse was covering it, but it's actually minus 21 degrees, not positive. You know how I knew that wasn't right is because I saw them both a couple of nights ago and they were right next to each other at my friend's house. When planets are located in almost the same location of the sky, that's known as a conjunction. Okay, our job is to find the constellation. Let's start with Mercury, 636, positive 18. Six 36, 10, 20, positive 18. Currently in Gemini. Right? 421, positive 17. 421. And what was it? Positive 10, positive 17. Do you see where we're at? Where are we?
Taurus.
Right? 15 minutes, 0, 15, and positive 2. So we dial it back to 0 hours. Ah, nuts. Hold on. Fiddlesticks here. There you go, you bastard. Okay. Oop. Sorry. 0, 15 minutes is a quarter turn. That's positive 6 or, oh, sorry, positive 2. Where are we? We are in this constellation, Pisces. Uh, 1942. So now we're swivel around to the other side. Okay. There's 19 1940 minus 21, negative 10, negative 20. Where are we? Let's see, we're down here somewhere, it looks like.
Sagittarius.
Okay. 2008, negative 20. So there's 2008. Ooh. And the boundary minus 10. That's really close. That's on a cusp. 2008 is just barely over the line in Capricornus. When a planet is on the boundary between two constellations, we say it's on a cusp, right? All right. I got one more little game to play with you guys. Now, in addition to being able to look at stars, you guys will notice that there's a little nubbin here that represents the sun. And the little ball that represents the sun can move along the dates of the ecliptic. And I want you guys to notice, it's kind of hard to see here. Dorcas Maximus, get this thing going here. All right. Notice that I can list dates, right? February, March. By the way, remember how we just did the spring equinox? There's March 21st. When the sun is located right there, it's 0 hours of right ascension and 0 hours of declination. Now, what I want us to do here, just above table 2, is I'd like you to write down your B-day, and I'm going to do mine too. Here's how I want you to write down your B-day. I'm going to do a month/day. So I was actually born on 4/20, believe it or not, okay? 4/20, April 20th. And according to the people who talk about signs, astrologers, 4/20 means I'm supposed to be a Taurus. All right. But there's your sign, and then there's your real sign. The signs that you guys are familiar with from horoscopes were actually cast by the Greek philosopher, mathematician, Ptolemy in roughly 500 AD. He had a book, an astrology book called Tetrabiblos, I believe. That's where most of your zodiac signs come from. And 500 AD was such a long time ago, right? It was, help me, 2020. I'm just that stupid right now. Minus 500 is 1,500 years ago. And during that time, the moon has caused Earth to undergo a gravitational wobble called precession. So the moon kind of tugs on Earth, and it makes Earth wobble like this on its axis. Because Earth is undergoing this wobble, it changes the relationship between the celestial equator and the ecliptic. So even though people say my sign is a Taurus, my real sign is likely something else. For instance, if I were to go over here to April 20th, you'll notice that on April 20th, I'm actually in the boundary of the constellation Aries. So my real sign is an Aries. Am I an Aries or am I a Taurus? I don't know. Why don't we try it with Yimmercy? Yimmercy, what's your birthday?
February 13.
Sorry?
February 13.
Okay. And what is your sign supposed to be, according to the sign lovers?
Aquarius.
Let's see what the sun was doing. Where was the sun on February 13th? Well, over here we'll move the sun to February 13th. February 13th is actually in between the 15th and the 20th. Okay, Yimmersy. In what constellation was the sun on the day you were born?
Capricorn.
So, in fact, the sun was not in Aquarius on your birthday, but in Capricornus. So guess what? You're a Capricorn now, okay? Jordan, how about your birthday?
February 3rd.
Oh, what? That's pretty close, right? What are you supposed to be?
Aquarius.
I have a feeling you're not going to be in Aquarius anymore. February 3rd is actually, yep, it's still in Capricornus. You can see the ecliptic line. So February 3rd would be like there. And the sun was in Capricornus. Same with you, dude. Who else do we have? What about Javante? Is that it? I'm still learning everyone's name.
Javon.
Say that again?
Javon.
Javon, sorry about that. I had to hide the non-video participants so that I could see the people that I could see. So I was trying to remember. Can you help me spell that again? Because that'll help me learn it too. It's like
yeah, A-V-A-N.
Javon. Okay, cool. And what's your B-day, bud?
May 21st.
And what do you
Technically, I'd be a Gemini.
Or actually, non-technically, you'd be a Gemini if you think about it, right?
Right.
We are the technical masters of space, not those quack doctors who call themselves astrologers. Let's see what was going on with the sun on on May 21st. So
I think my birthday actually falls on the first day of it, so I doubt it's going to be the same.
So May 21, you can see is right there where my finger is, right? So in fact, you're a Taurus. Sweet. You've all been given new signs and new personalities by me, okay? I have literally changed your destiny. How many professors can actually say that? Not many. Okay. All right. So I hope you've enjoyed learning about the locations of the stars. This is what you shall turn into me. If you did it on a doc, upload the doc. If you did it as a hard paper, snap a photo. By the way, any of those of you who had trouble uploading your labs, by the way, I haven't graded the labs yet. I was a bit of a slacker. There's an app that the students yesterday taught me about. It's pretty cool. It's called Genius Scan. Especially good for students with Macs, but if you don't have Mac, that's okay too. Genius Scan lets you scan the picture as a PDF, and then you can either upload it to Blackboard or email it to yourself and upload it to Blackboard from your computer. What I want to make sure is, let's see how we're doing here. I want to make sure that when you guys are turning stuff into me, I can actually see it. Oh, sorry. So let me share my computer screen one last time. This is very important. When I grade your papers, I need to be able to see your papers to grade them. Otherwise, I'll have to give you a 0. So currently, we have all these people have turned in Lab 1, and Brendan even turned in Homework 1. Okay. Let's see who's looking good, and let's see who's not. Evan looks good. I can see the preview. Nameri, I don't know if I said that right. That looks good. I can see it. Jordan.
I haven't sent that yet.
That's okay. I'm looking at your lab from yesterday. Jordan, that looks good. Oh, you were going to try to make your fonts a little bit bigger, right, buddy?
Yeah.
Yimmersey looks great. Remember, you guys have to upload both homework 1 and lab 2 today. Brendan, sorry. Brendan looks good.
So you just want that page, right?
Just that page for the lab. The homework you submit separate. Okay, Albert, I don't know if you're out there and can hear me, but here's the thing, Albert. I don't want to have to grade your homework like this, okay? So if you could please apply a rotation to that before you upload it, I would greatly appreciate it. I don't have to turn my laptop sideways to grade your paper. Other than that, at least I can see it. Harrison. Looks good. I got it. That doesn't look good, actually. Harrison, a lead digit can never be 0. 6 point, I think you got the number wrong too, 211 times 10 to the negative 3. If you copied that correctly, 1, 2, 3. Anyways, that's wicked wrong. I don't want to look into that. At least I can see it, I guess. All right. So far, everyone who's submitted stuff, I can see it, but Albert, maybe rotate it properly. Okay. Here's the plan, guys. Let's talk about it one more time. You're going to submit homework number 1, correct? You are going to submit, make sure you submit homework 1 to the homework 1 submission. Make sure you submit lab 1 to the lab 1 submission. Now, we're going to attempt to try, I guess, watching the recording on Tuesday. Is that the plan?
Okay.
I have the link already. I'll find it and I'll email it to you. Should I email it to you before Tuesday or should I email it on Tuesday? What makes more sense?
Before Tuesday?
Before Tuesday? Okay. Should I maybe, should you just watch it and get on with it, or do we need to have a pep talk? I'm just a little scared because I've never done asynchronous before, so I've never shown people a pre-recording, and I'm not sure how that's going to go. So have you guys had other class? Is this the only online class you've taken, or have you taken others?
I've taken others.
Okay, Yimmersey, so you might have more experience than me. So what was it like when you took the other ones? Is this how they did things? Was it live or was it pre-recorded?
We were in live. So she would have everything all set up, and we watch it on our own. She will have like due dates of the stuff that needs to be done and submitted by that time.
And did that work reasonably well? Was it an okay system?
It was okay. Because let's say if I'm not able to be here at the time that you need me to see it, she'll give us the whole week until we are able to be able to see it.
If I understand you, Yimmersey, that actually gives you more flexibility, correct?
Yes. Well,
Yimmersey, I don't know if you realize this, but that's better for me too, because if I already have the recording, I mean, I always have fun doing this stuff. I don't know if you guys can tell, but I love astronomy and I'll talk about it all day long. But if I've already said the same thing and recorded it, to say it again, I don't know, it's a little bit redundant, you know what I mean? So it's way better for me because I can work on other stuff if you guys can watch the pre-recording. But I want to make sure that I'm here for you. Do you know what I mean? Like, I don't want you to feel like I'm floating in the darkness. I need you guys to know that you could, and you, not only can you email me, you can even call me. I gave you guys my cell phone on the syllabus, right? So if you guys remember the syllabus, let me just show that one more time. Well, hold on, just a sec. Just bear with me, okay? 1020 syllabus. This is right on the blackboard. So I have my email, but that's my personal cell phone. And I don't mind if you guys want to text, because I know texting is how we talk these days to each other. You want to text me or even call me and say, hey, B, I'm watching the video and I'm kind of having trouble putting this thing into my calculator. And if it gets really necessary, we could even have a Zoom, just you and me, or me and Jordan, or the three of us, or whoever wants to Zoom. We could have a little kind of breakout session where we talk about how to punch stuff in. You see what I'm saying? But then you'll kind of watch it and go through it. I guess, you know what I'm really worried about? I'm worried that if I do this, that you guys won't watch it. That's what I'm scared about. I feel like I need to be here to kind of crack the whip. I don't know if that's true or not. If you did this in your other class and it worked, and that's good. So I think what we're going to do is we're going to try it, and then we're going to decide what we like. And everyone's going to be 100% honest, correct? All right. So maybe later today, I'll find the link to the next lecture. It'll have homework lecture lab. If you guys want me to log in at some point and talk you through a part, I'll do it. Otherwise, watch it, do it, and submit it that day on Tuesday. And then on Thursday, we'll meet up in the morning and we'll kind of talk about, did we like it or did we not like it? And we'll decide how to go forward from there. Because I have all the rest of them already recorded. Like you said, Yemmersi, that'll give you some flexibility to watch it at your own time, at your own pace. On the other hand, you guys might like some aspect of the live thing too. We can figure that out, all right? Okay, so I'll send that link in a little bit once I find it. Jordan, any thoughts?
I just submit the lab.
Oh, should we take a look at it and see if it looks good? By the way, guys, even if you're doing the pre-recorded labs, I'll at least want to check in with you guys live once a week for a few minutes to kind of talk about how it's going. You know what I mean? I just really want to make sure that you guys feel like I know what it's like when you're a student and you feel like the professor's just not there. I don't want to be like that. So I want to be really available for you. Let's see, you submitted lab 2. Let's see how it looks, bud. Yeah, that looks great. Oh, you even got the umlaut. Nice job. All right, cool. All right, are there any other things that we need to talk about? Anyone in the video chat or in the background? Concerns, issues, thoughts, questions? Can you think of anything? All right. I'm going to stop the recording.